questions will come up on the screen for everyone, and we'll walk through that until we get ready for the next group of 3 presenters. So again, I want to welcome everybody. I think we've got all the background taken care of, and thank you to everyone for participating, for sponsoring, for presenting, and with that, I think we're ready to get underway. Our first presenter this morning will be Dan Kaiser, talking about sulfur fertilizer and application rates. Dan is an associate professor in the University of Minnesota, focusing primarily on soil fertility and nutrient management, and I think been a part of this conference every year since you've been here, Dan. So thank you, and take it away.
All right, thanks, Warren. Get my screen shared here. Hopefully you can see it. So I'm just going to cover a brief overview of the talk I had. I'm not going to cover everything related to some of the things I was talking about in the talk with rate and some of the work when we were looking at different crop response to sulfur. I'm mainly going to focus on here just going through some of the source work, because I think it's kind of been the most critical thing we've been looking at over the past few years, has been looking at what's the most optimal sulfur source to be looking at to make sure we can maintain sulfur availability. So a source of sulfur at your crop, there may be some small amount of organic sulfur that's taken up, but generally the bulk of your sulfur is going to be taken up in the sulfate form. So when we're considering forms to apply, we have to make sure we have a form that's going to provide readily available sulfate. So products like ammonium sulfate, potassium sulfate, calcium sulfate, or gypsum, all are going to have readily available sulfate. But elemental sulfur forms, and it's been one of the major interests in me with this research, I've been looking more at those forms to see how well they oxidize into sulfate to provide sulfur for the crop. The oxidation process for elemental sulfur depends on temperature, moisture, and the size of the particles. The other thing that can come into play, we get a lot of questions on, particularly with products like Tiger 90, since it's 90% sulfur, is the distribution spatially of the product across the landscape. That if you've got a product like Tiger 90, which is 90% sulfur, versus something like, we'll just say ammonium sulfate, which is 24% sulfur, that you're almost 4 times as much product if you have the same granule size in a landscape and a better distribution of the product as a whole. So that's been kind of one of the questions with that particular product. The thing with elemental sulfur that is very important though, and that's one of the things I'm going to talk about, the product is hydrophobic, which means it does not dissolve in water. And that presents some challenges, and I'm going to talk about that because I think those challenges are really what are dictating how well this product is working in the bulk of our fields here versus some of these other things, because we've shown that our soils have the capacity to oxidize elemental sulfur. So it's not that it can't be done, it's just something else is happening. Then organic sulfur mineralization, we know that's been an important process. Some of the older literature would say roughly 95% of our sulfur came from the organic matter. We've seen that become less and less though, and that's why we need sulfur more readily across the state. And then a manure availability right now, it's not well known, but we'd assume about 65% availability is kind of what the assumption is with manure, although we know that different animal species can vary in terms of what forms of sulfur there, which may be more difficult to release or become available for a crop within a given year. So one of the key studies that I'm doing right now, working with Africa, we set this up starting back in, it was just a year or 2 years ago in 2019, looking at sources and rates of sulfur in continuous corn production. And I use continuous corn because that's tend to be where we see consistent responses with many of our studies. Where we did this, we set it up at 4 locations. These are plots where we're continually applying the same treatments in the same plots year after year. This data I'm showing right now are the source data. So within our sources, we have our control or our no sulfur treatment. We have Tiger 90, potassium sulfate, and you're going to see this MST. This is a product that is finely ground elemental sulfur that's co-granulated, or it's mixed with a fertilizer when it's being blended, when it's being manufactured. In this case, we have a product that's mixed with potash. And the reason I'm using potash is because we've seen that a lot of our phosphorus sources contain sulfur impurities, so it becomes very difficult to tease differences with rates out because we're getting some application of sulfur in many of our studies, which is blanket applications of Pease. So we're trying to avoid that within this particular study. So of these locations, Becker and Morris, no difference in terms of the sources. At Rosemont and Waseca, seeing some clear differences. And the main things that we've been tracking with this, if you look at Tiger 90, we'll just look at Waseca here in 2019, no difference between Tiger 90 and the control. Then a sizable yield increase to K-sulfate and also the KMST. So we look at elemental sulfur as this MST product versus Tiger 90. We're seeing a clear advantage of this co-granulated product versus the Tiger 90 or the sulfur bentonite product. You can kind of see Waseca here, these very large sulfur responses back in 2020. And kind of what we've been tracking is roughly about 50% availability or 50% as available for the Tiger 90 versus some of the other sources. So we're seeing where it's benefiting our crop. It's not clearly giving us less advantage than some of these other sources and these co-granulated products. At least this MST product, which is sulfur micro at about less than 40 microns, is giving us some clear advantages, which finely ground sulfur should be more readily available for oxidation within a given field. So what's happening here? This is one of the things that I said I've been thinking about a little bit. If we look at the elemental sulfur being hydrophobic, again, it's not going to dissolve in water. So if we look at the data, and I'm going to show you the rate data here in a minute, the larger the particle, say if this is our our pastille of Tiger 90 in something with a larger particle size, when the way this product is supposed to work is the Tiger 90 absorbs water, and the bentonite in the product will absorb water and it'll increase in size, and that increase in size then will disperse the elemental sulfur by that pastille fracturing. The problem with it, and I think what we're seeing, why we're seeing issues with that, is we look at a lot of our medium to fine textured soils. If you start looking at the porosity in those soils, we just don't have the capacity for that material to fracture. So it gets trapped in and squeezed together. And we know that with elemental sulfur, even if it's ground in finely or fine particles, if those particles are squeezed together, they act like one larger particle. So the more finely or fine textured our soils, the more difficult we're going to have, particularly when we're incorporating these particular materials. Versus these co-granulated products, if you look at these little specks here, I kind of want to represent the little specks of elemental sulfur in there. If we have a fertilizer material that fully dissolves, it's going to leave smaller particles out there. They're going to have more room to move and more space to react, where they're not acting like one larger particle within the soil itself. So in terms of difference, I think that's what's happening a lot of times with, particularly with Tiger 90, and what we're seeing essentially in some of our sandier soils is a better performance of this particular product. And I think a lot of that is just due to the pore size when we incorporate that product, that it just has more capacity to fracture and be reacted on by the soil microbes themselves. So rate data from that same study, look at Becker, we're seeing rate responses to 10 or 20 pounds, depending on the year. And again, this is across sources. So the elemental sulfur, if I look at the data, or as a Tiger 90, work just as well as any of the other sources. And it makes sense based on what I just said in terms of having just a greater capacity, I think, for those pastilles to fracture. Then the only other site we saw it was at Waseca response in 2020 to the 10 pounds. In most cases, what we're seeing where we do get a response is particularly with the source is that many of these cases, 5 pounds is enough. So we don't need a whole lot of sulfur in many of these cases to give us a very sizable yield response. But we have some of these sites that we see a pretty severe deficiency. And I think a lot of our issue at Waseca was an interaction between sulfur and nitrogen, where we're a little low on the nitrogen side, and you can compound a nitrogen and a sulfur deficiency together. They just interact very well together in terms of reducing yield. So updates to the guidelines. Back in 2020, when I made this last change, I did add one thing to the corn guideline. I added in poor drainage. I talked about this actually in the text more, but we're seeing more and more that poorly drained soils, we see a lot of striping in those soils, and we see situations where we need some sulfur. We don't need a lot. We know that with high organic matter, that 5 pounds typically, we were seeing that be a sufficient rate. So we know there's some consistency in there in more instances where we're seeing a sulfur response, and that's kind of the major changes. What I talked about in the remaining presentation that's recorded, I talked a little bit about soybean. In terms of recommendations, I don't recommend anything be applied unless we hit some specific circumstances. So organic matter less than 2% in situations where you're not putting a high rate of 20 pounds or more of sulfur on ahead of the previous crop, then it might be something you want to consider, because we know that soybean can scavenge some of that previously applied sulfur. Then with alfalfa, I showed some data in the recorded presentation, really tracking a couple sites where we're seeing some responses with it. What I recommend is, again, is 25 pounds of S and sandy soils. High production systems 10 to 15 pounds. If your organic matter is greater than 3%, and if you're below 3%, then increasing that to 15 to 25. So we're at least being able to track some of these things that we haven't been in the past. And really, the last thing to remember with MAP and DAP, they contain between 1 to 3% of sulfur as impurities. So that when you start looking at your total application rates, you're probably getting a few pounds with your Pease sources. So in terms of really pushing those rates to the high side, I really haven't necessarily seen that we need to go much more than 20, 25 pounds at max in many of our studies just because of some of this. So with that, just kind of remember, source of sulfur is probably the main consideration I'd be looking at when you're looking at making your purchases. Crop response is important, rate, and then also timing. So that's all I have. I'll take some questions here. I'll be back on at 9 for the Q&A session.
Very good. Thanks, Dan. We'll look forward to the Q&A in a bit. All right, our next presenter is Jeff Vetch. Jeff's going to be talking today about P&K applications, question, band, or broadcast. Jeff manages soil science research at the University of Minnesota's Southern Research and Outreach Center in Waseca. And again, a voice that's very familiar to this group. So good morning, Jeff.
Good morning. Thanks, Warren. So the question today that I'm going to talk about is why might we want to deep band P&K fertilizers? So I think the obvious things is when P&K soil test levels are low, that's kind of the key time, and that's where it's the most effective. In certain systems like strip till and no till, where it saves time and money as it's part of the same pass. And in these systems where we have very little tillage to incorporate phosphorus, it can very effectively reduce phosphorus runoff. And Nathan Nelson is going to show that in a presentation a little bit later. It can minimize stratification of these P and K immobile nutrients. That happens from broadcast applications and no tillage. This is generally more important in potassium than it is with phosphorus. And that's part of how plant K is taken up in the plants and recycled through the residue and back to the soil surface. It can reduce fixation of P and K, which makes it more available. We get phosphorus fixation in high pH soils with calcium phosphates and in very low pH soils with iron and aluminum. K can be fixed or kind of held by clay particles, illites, vermiculites, and smectites, and those are common clay minerals that we have here in southern Minnesota. Greater yields and fertilizer efficiency, and this has been shown by Ream and Lamb, and as they had banded K, increased corn yields in a ridge till system, but interacted with a hybrid. They had a response in one hybrid, but not in another. And then the economics. You can potentially use less fertilizer. You can increase your return on investment. And this certainly is important when we got rented land that's maybe run down and has low P and K soil tests, as I mentioned earlier, or when commodity prices are low. So the U of M fertilizer guidelines have significant rate reductions for using band versus broadcast applications for corn. At the top of this table, we have the soil test levels for P, Bray P, Olson P, and you see in the very low and low categories, we have significant reductions in rates of application for band versus broadcast, about 50%. That reduces the percentage a little bit at the medium soil test level, and even more so as we get to high and disappears as we get to very high. And the same is true for potassium. But there is no rate adjustment or rate reduction for soybean, and that's just based on data we've had in the past that just showed it wasn't necessary. We started a study in 2019 with a setup, and then in 2020 was our first growing season where we're looking at side-by-side comparisons of band versus broadcast applications at Waseca and Rochester on glacial till and silt loam soils in Rochester. This picture here on the left, this plot received 60 pounds of K2O per acre or 100 pounds of potash as a broadcast. It has a soil test of 84 part per million ammonium acetate K. The slide on the right has also received 60, but as a band, and the soil test is very similar. You can clearly see the growth differences, the better, healthier colored corn. And in this little picture on the inlet here in the lower left, you can see potassium deficiency quite clearly in this leaf. And that was quite evident in this photo on the left, and you could not find any of it here in the band application on the right. Here's another photo and a phosphorus comparison at Waseca. This was taken a little bit later. The corn's a little larger. That fiberglass rod separates the plot. On the left, we've got the band, received 45 pounds of P2O5 per acre. And on the right was the broadcast. And again, you can see taller corn, greater leaf area, and healthier corn. It's interesting that the soil test here on the left is 2 part per million, on the right is 3 part per million Bray. These are very low soil tests. Soil tests, you have to kind of mine your field down to get to this low levels. So this table, we're going to look at some responses we saw, and these are on fertilized plots. These plots received fertilizer in 2020, and the first 2 comparisons is the band versus broadcast for potassium. These plots, it was a set of 4 side-by-side comparisons with a range and soil test. They received either 45 or 60 pounds of K2O per acre. When we look at the comparison of these plots in a factorial ANOVA analysis, the soil test levels in June of 2019 prior to application were very similar. So that's what we want. We want a side-by-side comparison of similar soil tests. The ear leaf K at R1 tended to be numerically greater with ear leaf or with banded application than broadcast, but you don't see any letters here, so that's not a statistically significant difference, as what we saw with the yields. Numerically 4 bushels difference, but not statistical. Now these next 2 treatments were part of a different analysis, so we can't compare them per se to these 2, but we can compare them numerically. The first one is a treatment that has received 60 pounds of K2O per acre broadcast annually since 2012. And this one below it has received 120 pounds broadcast since 2012. We see the 60 has a higher soil test and the 120 much higher. We look at the ear leaf K for the 60, it's similar to these where we banded or broadcast, even though the soil test is higher. And the 120 has a much greater ear leaf K or concentration. When we look at yield, statistically, I don't think there's any differences in here, but numerically, you might see a difference here between this 61 and this 120, where we have 229 to 241. But our banded treatments produce pretty similar yields compared to this 120-pound treatment annually with a lot less fertilizer. At Rochester below, a similar comparison, 4 treatment pairs. Soil test levels were very similar prior to application. Ear leaf K tended to be greater with the band application, but not statistically different. But yields were 6 bushels difference, and that was a significant difference at Rochester. What's interesting as we go down here to these annual treatments, and again, you see the increase in soil test, the increase in ear leaf K, but no difference in yield. Even when we went up to this 120-pound treatment annually for 7 years, where we had a soil test level over 200, ear leaf K over 2.07, and yield was still very similar to these over here, and statistically not different than the banded K with much less treatments or much less fertilizer applied. So these charts are looking at, we used 6 treatments in the previous chart that were fertilized. These are the other 6 treatments that did not get fertilized in 2020, but will be fertilized for the 2021 growing season. And the purpose of this is to look at the response to soil test K for both grain yield and ear leaf K. So here on the left, we have grain leaf or grain yield on the y-axis and soil test on the x-axis. The circles are the Rochester sites, and you can see we had a range in soil test levels from about 145 up to about 175, and there's really no difference in yield across those soil test levels in those unfertilized plots. At Waseca, the triangles, you see there's a trend towards some of these lower soil test levels down here in the 120 or less than 130 to having somewhat lower yields, and it get a little bit better when we get up here into the higher soil test levels. What's really interesting is when you go over here and look at ear leaf K, and the effect of soil test level on ear leaf K is it clearly increases as soil test level increases, not what we saw in yields. And another interesting fact is that the critical concentration for ear leaf K at R1 is between 1.7 and 2.5%. That's this shaded box. None of these treatments reached that shaded box, even though we didn't really see any yield differences at Rochester and only modest yield differences at Waseca. So now we're going to switch to phosphorus, and this is again the fertilized treatments. We had 8 comparisons. These 8 comparisons received either 30 or 45 pounds of P2O5 per acre. We had soil samples prior to application in June of 2019 and June of 2020 after application. We see no differences between band and broadcast, which is what we'd expect. Prior to application, we see an increase in soil test level, which meant that we measured some of that added phosphorus for the second year, or for this year growing season. But at Waseca, we had no difference in ear leaf concentration and no difference in yield. At Rochester, the pre-samples were the same. The post samples, the banded was a little bit greater than the broadcast. And this is one of the challenges of banding fertilizer, is trying to get soil samples or soil test data that represent the field. And in this case, we saw an increase in soil test level with the band versus the broadcast, even though these plots were receiving the same rates. The ear leaf P was a little bit greater with broadcast, but again, there were no differences in yields from the phosphorus study at Waseca or Rochester. Go back to the unfertilized treatments. There was 8 of them, and you see it's pretty flat all the way across here, certainly flat for Rochester and fairly flat for Waseca, even though there's a wide range in soil tests from 6 part per million at Waseca up to about 28. The only treatment that looks like it had a yield penalty is this one right here that had a soil test level of 6 part per million. We look at the ear leaf phosphorus at R1. The critical concentration is 0.2 to 0.4, so most of them fall inside the box. And again, you see that trend towards greater phosphorus concentrations as soil tests increase, but we're really not seeing much difference in yield other than this one treatment, which ironically is this plot right here, or this treatment right here, which did test below the critical concentration. So our observations, to kind of summarize, we did see growth differences. They were observed at Waseca and for both phosphorus and potassium, and at Rochester for potassium. And when we did, the band was always better than broadcast. We observed K deficiency symptoms. Most were in the broadcast treatments. We had a small yield response to banded K at Rochester, which agrees with these previous research. We did not find a yield response to seed placement in either location. And from an economic standpoint, can we use less fertilizer? Maybe, but this is just year 1. We're going to need at least 1 or 2 more years to make that call. Over here on the right, I just want to caution, when we look at these plant tissue tests, we need to just not overreact to low or marginal, especially for K tissue tests. As you can see, in this study, we didn't even see much of a yield difference, even though there was a wide range in soil test K, and all those tests in the unfertilized plots came below the critical threshold. Also, there in the phosphorus soil test, we had much higher P, ear leaf P at Rochester than we did at Waseca. So it suggests that hybrids and environments can make a difference as well. I'd like to recognize AFREC and the U of M Experiment Station for funding this, and also Dan Kaiser, Kyle Holling, for their contributions, and my summer intern research staff for helping out with these projects. And I'll be available in about 10, 12 minutes to answer questions. Thanks, Warren.
Very good. Thank you, Jeff. Appreciate it. All right, our next talk is going to be on the latest research in nitrogen and phosphorus credits for manure. And so I want to welcome Melissa Wilson. Melissa is the Manure Management Specialist at the University of Minnesota in the Department of Soil, Water, and Climate. Good morning, Melissa.
Good morning. Can you see my screen okay?
Yep, it looks good and sounds good as well. Thank you.
Great. Hello, everyone. Today I'm going to talk about one of our favorite topics, nutrient crediting from manure. Hopefully you were able to see my video that will go into a lot more detail about some of the setup of this study that I'm going to talk about. But to give a summary, this is a study that we started back in 2018. So it was one of the first sites that we set up. And we wanted to understand if the nitrogen and phosphorus availability that we currently recommend for different manure types is still accurate. with the changing weather conditions that we've been seeing, as well as some of the new equipment, whether it's liquid solid separation or new application equipment. We wanted to see if these are having an impact on availability. So we set up at 2 different locations. We had the Southern Research and Outreach Center at Waseca, Minnesota, and then we had some at the Southwestern Research and Outreach Center in Lamberton, Minnesota. And then at each site we had, or each location, we had 2 different sites because we wanted to start or apply manure in 2 different years to see if there were different weather impacts. So we started site 1 in 2018. And just recently, this is where we are today. We just finished up those sites at both locations. We also started a site in 2019 at both locations. So we have 1 more year of those to go. And what we did is we applied 6 different manure types. We looked at a bedded beef pack, liquid swine finishing manure, a raw dairy manure, a liquid separated portion of that same dairy manure, turkey litter, as well as a composted chicken layer manure. And we used our current recommendations for the nitrogen and phosphorus availability to apply what we thought was 140 pounds of first year available nitrogen. And then what we did is we had separate fertilizer plots where for some of them, we just changed the nitrogen rate. So we had full phosphorus, full potassium, full sulfur, and we applied different nitrogen rates from 0 up to about 120% of current recommendations. And then for the phosphorus plots, we did the same thing, but for phosphorus, we did full nitrogen, full K, full S, and then we applied from 0 up to 90 pounds of phosphorus. So I'm going to go briefly over some of the results. One of the things, I'm not going to talk about yield just due to shortness of time, but I want to talk about like the fertilizer equivalent value that we saw from these different manures. And we have a little bit more information right now on nitrogen. We're still waiting to get back some of our phosphorus information. So I want to cover what we did with nitrogen. What we see here is nitrogen uptake in the corn. This is in stalks, cob, and the grain. And this is our different manure sources at the bottom. And then we compared that to the nitrogen uptake of the corn at various nitrogen fertilizer rates, which we see at the bottom of this graph, from 0 up to 168 pounds of nitrogen. And remember, we are aiming to go for 140 with our manure. So it should fall out somewhere between these 2 rates. And it didn't. So that was our first surprise. Of the highest nitrogen release was with our swine manure, chicken layer manure, and turkey. Our bovine species, our beef and our dairy, we did not get nearly as much nitrogen released as we expected. So one of the things that you can do is when you have a nitrogen rate curve like this, you can develop a response curve. And that's what we did here. We developed an equation. And then since we know how much nitrogen uptake we got with manure, we can take that out over where it lines up with this equation. And then if you take it down to the x-axis, you can get what the nitrogen rate or the nitrogen fertilizer equivalent value is. So if we also use this equation. So basically we know what y is and we want to solve for x. And that's the nitrogen rate at the bottom here. So I want to talk about the differences in the 2 different sites. And this is just for our 2018 data. As I mentioned, we're still organizing a lot of data for all of these different sites. But what we have here is our nitrogen fertilizer equivalent value. And remember, we were aiming for 140. And you can notice that we did not get 140 in most of these cases. And what I have over here is that nitrogen fertilizer equivalent value divided by the total amount of nitrogen applied. We had we had manure tests for all of these. So we know how much total nitrogen was in the manure. And we multiplied that by the application rate to get the total nitrogen applied. And this is how much nitrogen was available. And this is how much nitrogen we assumed was available based on our current guidelines. So for instance, for swine finisher manure, the way that we broadcast it and then incorporated right away, we would have expected about 75% of that total nitrogen to be available. We only got about 40% in that year. You can see that most of them are pretty low. And this is at the Lamberton site. Waseca, on the other hand, still low in most cases, but we did get much more nitrogen out of this site than we did at the Lamberton site. Here's our nitrogen fertilizer equivalent value. Here's our percent nitrogen that was available versus how much we assumed was available. So for all of these, you can see that these percent nitrogen available was much higher at Waseca. And the one thing that was interesting was our composted chicken layer was actually higher, more available nitrogen than we assumed. So that was kind of an interesting turn of events. The one that was a little bit lower than our Lamberton site was our bedded beef pack. At Lamberton, we got about 6% availability, but at the Waseca site, we got a little bit less at 4%. So just want to talk a little bit about our second year nitrogen availability. We're still waiting on some of that nitrogen uptake data. Because of COVID, we were about to send our samples out last spring to start getting analyzed, and then things happened and we weren't able to get those out before everything started to shut down. So we're still waiting on some of that data this year. But I'll show you corn yield. So we have from 0 to 200, and this is at Lamberton. Here we have our yields for our different nitrogen rates, and then we have our different manure types. And if I show you, if I highlight this bar between where 0 nitrogen was applied and 49 pounds of nitrogen was applied, you can see that most of our manures fell in that range. So we are seeing a second year credit from that manure, likely, except for soy manure. Soy manure is right on that edge where it was hanging around 0. And here's our Waseca sites. We see a very similar trend. The yields were a little bit higher. But if we highlight this area between 0 and 49 pounds of nitrogen, we can see that, again, most of our manures are giving us a second year credit. And interestingly, beef was one of the ones at both sites that gave us very low first year credit of nitrogen, but it was one of the higher second year amounts of nitrogen available. So it was kind of compensating at least a tiny amount. The only difference with Waseca is that our soy manure was actually releasing definitely on that 0 end of nitrogen. You can see there's some variability there, but our soy manure did not seem to give us a second year credit in this particular site. So one of the things I want to remind you is that 2019 and 2018 were very, very wet years. In fact, we thought 2018 was bad and that it couldn't get worse. And then it did get worse because 2019 happened. And in 2019, we also had issues getting planted. So, the smaller corn and reduced yields just from that probably affected some of the results from the study. So overall, we got less nitrogen uptake than we were expecting from our manures. And we did notice that there does seem to be second year credits, except for maybe with a soy manure. We have to look more into that, especially once we get the nitrogen uptake information. And some of the other information that we're hoping to gain from this study is, where did the nitrogen and phosphorus go? Is it still in the soil? Is it out of the soil? We have a lot of soil samples. We took 2 to 3 soil samples over the growing season down to at least a foot. And then we took post-harvest samples down to 3 feet to try to get at some of that nutrient cycling. What form was it in? Was it in an organic form? Was it in an inorganic form? So you can hopefully better understand some of the fertility and cycling issues throughout the growing season for each of these different sites. So that was a quick summary. I'd like to thank AFRIC, the Minnesota Ag Fertilizer Research and Education Council, for funding that. The SROC and SWROC crews, as well as my staff, are integral in getting this accomplished. This shows us our Waseca site. You can see site 1 and site 2. So it was a pretty complicated study, and I'm thankful for having awesome people to work with. Here's my contact information. If you'd like to see more of our research that we did this summer, check out this link to do that. And I think hopefully we will start having some time for questions.
Very good. Thank you, Melissa. And you're exactly right. At this time, we'll have a short Q&A session for the first 3 presenters this morning. So for Dan Kaiser, Jeff Fetch, and Melissa Wilson. And so now you're seeing, all of you should be seeing the Slido screen. And so we're going to take these just kind of in the order that you guys as participants have upvoted them. So first question, what are your thoughts about using gypsum as a S source? And so this, Dan, I hope you're back. There you are.
I'm here, yeah. It's a fine source to use. I mean, in terms of, there can be some differences in solubility of some of the products, but it is a sulfate source. So if you're looking at it in terms of comparisons to the other sulfate sources, it's fine. I mean, it won't have the acidifying effect that AMS has. So there's some positives there. But in terms of use, if you don't need the nitrogen, it's a source that certainly I would consider.
Very good, thank you. Next question relates to manure. So Melissa, how much estimated nitrogen is lost in poultry manure piled from December to April in field?
That is a good question. We haven't looked too much at losses from storage on my end of things. I usually look at the land application side. I would expect from December to April that it would be certainly lower than it would be if you're stockpiling it over the summer when it's warm, because volatilization, which is the nitrogen loss as a gas, tends to happen quicker at warmer temperatures. So I think it would be small. It wouldn't be zero, because we do know that as we get freeze thaw and as the sun warms up, like the top surface of the pile, we might still get some, but it would certainly be low.
Very good, thank you. And our next question again relates to manure. It's two-parter. Have you worked with the new John Deere manure sensor and VRT manure? And then the second part, what is a respectable timeline for changing the UMN manure NPK uptake guidelines?
Good questions. So the new John Deere manure sensor, I haven't worked with it personally. I've gotten to see some demos of it, and I've been talking with some of the people who are using it in the state. It seems like pretty exciting technology. The science behind it is pretty sound, particularly as we're looking at how it measures nitrogen. The big questions are, how are people going to use it? One of the things about manure is if you apply a straight nitrogen rate, you might get variability across your field in phosphorus. And phosphorus is a little harder to correct than nitrogen. So will people start moving towards applying a blanket phosphorus rate and then adjusting with fertilizer as needed for nitrogen? It's kind of interesting to think about. So it's hopefully something we'll be doing in the future. As for a timeline, I would say we still have another year on this study, and we'll always be kind of tweaking things and updating things as we get more information. One of the things about this study is that it was done in 2 really, really wet years. So now we have a lot of good data for what happens in wet years. We'd like to get some more information on dry, which requires more studies. But one of the first things I think we'll probably start doing is looking at the ammonium amount in the manure, because I think that will start getting us towards some of those differences between like a bedded beef versus a liquid beef if we have like a deep pit system.
Very good, thank you. Dan, I'm assuming you probably been able to read that next question relating to sulfur and applying 1/3 of the sulfur needs in the fall, 85% elemental, and the remainder or AMS at V3, V4. Can you address whether that's enough and the right timing?
So what we see essentially is the crop by about V5, V6 needs about 5 pounds of sulfur in terms of total uptake. So if you're looking at overall needs, as long as you have at least 5 pounds on up through about V5, you should be fine. We've looked at side dressing AMS, top dressing it up to V5, V6, and I've been able to have my whole load of sulfur on at that point in time and get maximum yield. So with only 1/3 of it applied as elemental in the fall, if you apply 2/3 as AMS at that V3, V4, you should be fine, as long as it's supplying around 5 pounds.
Okay, and while you're on the platform, we have the second question there now in priority relates to sulfur as well. And have you looked at the effectiveness of sulfur in the spring versus applied at side dress? And you may have just answered that if you want to expand a bit.
Yeah, we've done that spring versus at planting versus a top dress, and it's as effective. The only difference I've seen with it is our grain moisture was a little bit higher with the side dress or the top dress later in the season. So it likely slowed or delayed our maturity a little bit, but overall the yield potential was still the same.
Okay, thank you. Next question, and this one relates to injected liquid hog manure. So Melissa and Jeff, you watch too, because I know you've done some work on manure down there. But working with injected liquid hog manure, what do we know about first year crop availability of PK and S?
Yeah, so for phosphorus, we assume it's anywhere from 80 to 100% availability. Phosphorus tends to be in the inorganic form when it's in manure, at least the majority of it is. So that releases fairly quickly. Potassium, we think it's anywhere from 90 to 100%, because again, potassium only exists in the inorganic form. There's no organic potassium in manure. So it releases pretty quickly. And some of this will depend on soil type. Soils that have a high pH and have a lot of calcium in them might tie up more of the phosphorus than an acidic soil, for instance. For sulfur, we just don't know as much about that. There's not really great testing techniques for manure to find sulfate values, because there's a lot of interferences, as you can imagine, in manure. So as Dan mentioned earlier, we think about 65% or so of the total S is likely available, but it probably changes with different animal species. And that's something I'd really like to start looking into, is how we can figure out different tests for sulfur to get better at that availability.
Very good. Jeff, anything to add?
The only thing I would ask is Melissa, when we look at applying manure at nitrogen rates, how much sulfur are we typically applying? Do we think we have plenty?
Generally speaking, I think probably yes, if we're at the nitrogen rate. I was just looking, there was another question later about bedded beef pack and sulfur. I know in the bedded beef pack, we were on average, I don't have many samples, but I have a couple, and it was from 2 to 3 pounds. So if you're applying that at 20 pounds per ton, so if you're applying 20 tons or so, then you're getting 40 to 60 pounds of sulfur. So in that case, you're probably having enough sulfur.
Very good.
Yeah, and I
Thank
guess
you.
with swine manure, I think you get a lot of reduced sulfur forms. So I think the availability of some of those pit manures can be slightly less. The bedded beef, I would suspect, are going to be more easily mineralizable, but it's, as Melissa said, it's a researchable question that I don't know if anybody's looked at.
Very good. And then Dan, if you'd continue on and talk a little bit about alfalfa and sulfur sources in high organic matter soils.
So I think this question, you're talking the top one, Warren, here.
Yes.
This one deals with a few of the sources we've been looking at with these MST products, because we've been testing a couple products that are either blended with MAP or 1152O or with MOP, which is potash. So that's the one we used actually in the study that I was referencing that I showed. In terms of differences between the products, they're roughly the same total sulfur content. I haven't seen too much of a difference. Site by site, if you look at all the testing we've done, they've bounced around, or one's better than the other, but on average, there's not a lot of difference, between the two. It seems like just having that sulfur, the more finely ground it is in those co-granulated products, the more quickly that elemental sulfur is going to react. And I was a bit surprised with some of the data we had. I thought we'd see those products lag a little bit, but they seem to be performing well and giving us another option, at least an elemental sulfur option, other than some of the products that are out there. So I would suspect, again, the MAP MST or the MAP based product would perform just as well. And we have data to show that. I just didn't summarize any of that.
Very good. Thank you. And Melissa, you've talked about this a little bit, but the question relates to that beef pack bedding. Are there concerns around sulfur associated with that source?
Yeah, as we kind of talked about with that, when we're getting 2 to 3 pounds per ton, I think and as Dan mentioned, it's likely more soluble because it probably has a little more oxygen in the pile than like a deep pit swine does. I'm not thinking so, but it is something that we could potentially look at in the future because it does have certainly a lot of bedding in it.
Very good. Thank you. I'm going to skip this next question because I think it actually needs to go into a later session, but we will hang on to it. Don't worry. And go to the next question for Jeff. For someone who rents land and they ban in-furrow, you're applying less. The grower gets what they need, but the landlord may perceive that they're having their farm mined in a way. So how would we best educate landowners on the benefits of banding?
Yeah, I think that there's 2 points I'd make there. One is the rate of the band is important. If we're going by the guidelines and you have very low soil tests and you're at that 50% of the broadcast application, the soil test level probably will maintain, but it probably will not build. In a long-term study that we did with phosphorus, where we started out in a medium soil test level, all we need to do is apply about 30 pounds of P2O5 per acre to maintain the soil test level at that in those medium categories. The other thing would be is if you reduce that rate to more of a starter rate of 15 to 20 pounds of P2O5, we've got data that would show the first maybe 2 to 4 years, you're not going to see much of a soil change. But then after that, you're going to start to see the soil test decline. And it'll probably decline about 1.5 to 2 part per million per year. And we actually have quite a bit of that data. If the grower wants to reach out to me, I can send it to them if they'd like to share it with their landlords.
Very good, thank you. We've probably got time for one more question. And Dan, we've got a viewer wondering, on heavier soils, does 30 pounds of Tiger 90 every other year supply enough S to the corn, or does it never break down enough to be enough usable sulfur?
Well, a lot of the data we have shows that it's at oxidation issues. I mean, I think the thing is, let your crop tell you. Look at it. If it's deficient, normally we see some striping up through, V4, V5. And if it greens up by about V5, you should be fine. But if you continually see some striping beyond that, then it's probably not enough. So that's going to be kind of the telltale. I think, is just let the crop tell you. Gut feeling on kind of what we've been seeing. That's one of the reasons we're doing this long term with this new study, is to kind of see whether or not continual applications over time will provide some benefit. But you look at a lot of our data, it's still underperforming compared to the sulfate sources. So as I said, just scout your crops. If you see striping, if it's getting to V5, V6 and it's still not going away, I would put something on, and then I would start looking at maybe adjusting your tactics for sulfur application.
Very good, thank you. So we're going to stop there, and I will just say that if you've got a question in Slido that we did not get to, we'll ask our presenters to go and look through, and if there's one that pertains to you and you have an answer, if you could just type that in quick for the questioner, and then we will move on to our second group of presenters. First up, in this next group, we're going to be looking at cover crops and how they fit into and affect nutrient management. So our first presenter, Lindsey Pease, phosphorus and cover crops in the Red River Valley. Lindsey is an assistant professor and extension specialist in nutrient and water management based at our University of Minnesota Northwest Research and Outreach Center in Crookston. Welcome, Lindsey.
Thanks, Warren. I'm just pulling up my presentation here. All right. Okay, so my talk is really going to kick off kind of 3 presentations talking about this phosphorus and cover crops. So my topic is looking at phosphorus and cover crops in the Red River Valley. And, just to kind of set this up, we know that cover crops have a lot of benefits, and they do really provide a lot of good to the landscape. But they are something that they're not just like a plug and play crop. They also require a lot of management. There are a lot of factors that you need to think of if you're going to be implementing cover crops. And I think one of the pieces of the puzzle that we don't really think about maybe quite enough is this kind of fertility management piece. How are you going to layer your fertility strategy for your cash crop on top of this cover crop management? We're really focused on kind of some of those, like just establishing the cover crop, getting it on. But really the point of this presentation is, even though we're going to talk about some phosphorus loss from cover crops, it really is to kind of get everybody thinking and thinking about what happens to the cover crop residue when it's out in the field. So this experiment was primarily a lab experiment that was done by Dr. Albert Sims, who was my predecessor in this position at the Northwest Research and Outreach Center. He looked at 3 species of cover crops that they planted following a fall fertilizer application. They did 3 application rates, 0, 75, and 150 pounds per acre of P2O5. And then they grew buckwheat, radish, and cereal rye. And then this vegetation was sampled in the field, and then it was taken back into the lab and frozen. So it was allowed to grow for a little bit, and then taken back and frozen in the lab. So this slide just shows kind of some pictures of what they actually did to the frozen cover crop residue in the lab. Basically, it was submerged in water to kind of simulate a flooding event, and then that water was drained out of the jars, and the concentration was measured after 1 day. And then they repeated this for every 4 days. They replaced the water, then drained it out again, and then just looked at the raw concentration. So I will say, this kind of represents almost like just like a really straightforward look at like what is the potential for phosphorus release from the cover crops. So this graph is really busy. So I'm just going to go over it briefly, but I talk through it more in my video. So I'll give a quick plug to go back and watch the video if you want to dig in a little bit more to this graph. But what we're seeing overall is that after the first 24 hours, you really do get a big pulse of phosphorus released from that frozen cover crop residue. And even though that level declines after the second submergence, the third, and the fourth, there still is, a considerable concentration released. It's not zero, which I think is important. Now, a lot happens to this water between the time it would be released from a cover crop, to the time it would make it into a stream. But I do think it's important to think that it's not zero. And I think later the presentations that Marin and Nathan have will do a little bit more talking about what happens to that concentration once it gets into the field. But again, this is looking at kind of what's being released from the plant itself. And I also threw on a couple of lines for reference onto this slide. And the dashed line at the top for dissolved phosphorus, that's what the concentration that we consider is potentially harmful to aquatic life. And the line at the bottom for total phosphorus, that's what's recommended by the International Red River Board at the US-Canada border. So that's what we don't want to be releasing up the river to our friends in Manitoba, just specifically for Northwest Minnesota and northeastern North Dakota. And again, a lot happens to this water from the time that it is kind of it would be submerging the crops and have this high concentration. So if you imagine that jar of water or a fishbowl sized amount of water, and then you throw that into a river, obviously this concentration would be getting diluted over time. So just make that point. But it's high enough that it's something that we do want to think about. And so then how do we keep that phosphorus that's released from the cover crops if we know that it's going to be released from the residue? What do we do to keep that in the field? Well, we want to make sure that we can tie that up in the fall. And then we also want to make sure we keep the soil and water in place in the spring. So what I mean by tying it up in the fall is, the first kind of time of the year when we see freeze thaw events in the Red River Basin is as early as mid-October. So you want to make sure that when this freeze happens, there's sort of capacity in your soil, there's buffer space available for it to capture. And this timing might be a little bit different if you're in, southern Minnesota near Iowa than you are up here. But for us in Crookston, it usually happens about mid-October. And the way that we make sure that we have binding sites in the soil is to listen to the studies that Dan and Jeff participated in before I got on board. But these long-term phosphorus experiments that were done all throughout the state that really show that just as Jeff just mentioned, if you are applying that kind of 30 pounds per year of phosphorus and you aren't building those soil test levels, then that means you have binding space. But once you get to the high or very high levels, then you need to start thinking about the potential for binding sites. And again, I won't spend much time on this slide here in this talk, but these are questions that, especially while we have Jeff and Dan on board, they can also help answer. So in addition to making sure there's capacity in the soil, you also want to then, once you've bound it in your soil, keep that soil in place. And this is a little bit one of those things where cover crops actually could be part of the answer to keep the soil and water in place. And you know, and I think having those living roots in the ground to sort of stabilize everything is a potential solution to the problem. It's certainly not, you know, the only way to keep soil and water in place. But these are just kind of some of the questions and the trade-offs that we need to think about when it comes to kind of this issue of phosphorus management. And so with that, I think just to summarize, you want to, again, if we know that the frozen cover crop residue is going to release P at potentially a time that there isn't a growing crop out there to take it up. So if you have those winter kill cover crops, they might release P, and then you need to make sure that number one, you have capacity to keep it in the soil, and number two, that you have the ability to keep the soil and water in your field so that it's still in the field of when you plant in the spring. And just quick acknowledgements. Of course, Albert Sims designed the experiment, and I've been working a lot with Anna Cates on kind of this data analysis and interpretation and turning this into really useful and usable information for all of you. So this work is still ongoing, but this is just kind of a teaser, and I'm really excited to, you know, for this to pair with Marin's experience and with Nathan's experience in other parts of the country, well, and of North America, just in Marin's case. So.
Very good. Thank you, Lindsey. Appreciate it. And we'll continue this discussion of cover crops and phosphorus movement and the like. Our next presenter is Marin Mcrae. Marin is a professor of geography and environmental management at the University of Waterloo in Ontario, Canada. And so we continue expanding our reach a little bit. So good morning and welcome, Marin.
Hi, good morning. Thank you. It's a pleasure to be here. I'm just going to share my screen. Okay. I just want to make sure that you can see.
Yep, we can see it, and you're coming through just great.
Excellent. Thank you. Okay, so thank you. Yes, I'm going to talk today about phosphorus and cover crops in Ontario. I'd just like to acknowledge my co-authors, Tatiana Lozier and James Kober, who are two former master's students, and my collaborator, Laura Van Aert, who's at the University of Guelph, and of course, some funding agencies and partners along the bottom. Okay, so many agricultural systems experience winter and snowmelt. So you can see from the map on the screen, you can see these are the regions in the Northern Hemisphere that are experiencing a lot of prolonged or decent amounts of snow cover and frost. And of course, today is a little bit more extreme. This is looking at in Ontario and the Great Lakes region as late as late March. You can see that we're still really, sorry, my slide bumped ahead and I'm trying to get it back. Sorry, guys, my thing is not working very well right now. Give me a second.
It's the cold.
Is it? I don't know. It's not done this to me before. Okay, is that working now?
It is back. Thank you.
Okay, sorry. Yes, so although we do have this winter snowmelt, we don't understand as much about phosphorus mobilization during this period. I think a lot of our BMPs and a lot of our management practices historically have emphasized other times of year. So we have to turn our attention to things that are going to be effective during the non-growing season, particularly during those critical snowmelt periods. Although we're trying to learn more about that snowmelt period, it's important to realize that not all winters are equal. So cover crops are something that show promise to build soil health. Lindsey talked about that a few in her presentation, but they also have the potential to reduce phosphorus loss and runoff. Unfortunately, some studies have shown that there's a risk of enhanced phosphorus loss following freezing conditions in winter, because the plants freeze, they lyse, and then they can release this dissolved phosphorus to runoff, particularly during that critical snowmelt period. I'm just learning that there's timing on my slides that I can't seem to get rid of while I'm on screen in front of all you people. So it's important to remember that not all winters are the same. So when we look at the Northern Great Plains, we look at areas, say, in the Canadian prairies versus the Great Lakes region, we see that we actually have very big differences in our climate conditions. We get a lot more precipitation out here. In particular, we get a lot of snow and snow cover, as you can see from the photographs. The other thing is that although we don't get the same plunging temperatures, we still get reasonably low temperatures. If you can see on the graphs on the screen, the red line is showing you the air temperature, but because of our snow cover, we tend to not see as much frost in the subsurface. And so our crops are not necessarily going to be subjected to the same temperatures that they might be in areas such as the Northern Great Plains, particularly in, say, Winnipeg and areas like that. And so when we start to think about the effects of freezing on cover crops and their potential to release phosphorus, we want to make sure that we're actually thinking about temperatures that are representative of the conditions that we actually see. So today I'm going to talk a little bit about some of the edge of field data as well as the experimental data that we've collected in the Great Lakes region to provide insight into the relative efficacy of these crops in this region. So the first question, do cover crops release phosphorus following freezing? The results of some laboratory experiments that we did. So if we direct ourselves to the left, we found in all of our experiments, we found that yes, cover crops and crop residues lose phosphorus after freezing. Crop residues like winter wheat don't release nearly as much as the cover crops do, but the amount of phosphorus that is lost really depends on a lot of things. First, it depends on the crop type. If you're looking at oilseed radish or oats, so some tender crops, yes, they're going to release a lot more than, say, red clover, cereal rye, or hairy vetch. Okay. But so hardier crops seem to be able to handle things and not release as much phosphorus. We also found, though, that it is affected by frost severity. So our experimental treatment that James Kober used was -4 to +4, as opposed to -18 to +4. And so this is really what might be experienced under the snowpack in the Great Lakes region. And so we can see that when you look at the moderate frosts that we typically experience, our cover crops are not at risk of releasing quite as much as they might be in a more severe climate. So crop type, freeze thaw magnitude is important. We also found that termination is important. If you terminate using a herbicide, it will release things. So crops that might have done well and not released anything, even under cold conditions, if they're terminated, they will release things. So that gives insight into, should you terminate in the fall or leave things green? So it may be that you should leave it green in some regions, or in regions where you know you're at risk of losing it, you could terminate ahead of time as a premeditated strike to try to release that pool before that winter runoff comes or that spring runoff comes. Now, another feature that we looked at, which is related to some of the work that Lindsey was talking about, is degree of moisture contact. And what we actually found is that when cover crops in the field setting, we did this experimentally, were rained on, so that might be sort of upland areas that are not prone to flooding, they release a lot less than cover crops that are subject to prolonged, say, 24 hours or more flooding in a field setting. So if we, in these areas that are they're prone to being inundated by water. These are areas where the cover crops in the spring are at far greater risk for releasing phosphorus following a freeze-thaw cycle. So yes, cover crops can release P after freezing, but it depends on a lot of things. So in a field setting, both of these studies, experimental studies, were coupled with a field component. So Tatiana Lozier had litter bags out in the field setting that she retrieved throughout the winter and extracted to determine how much water extractable phosphorus was left in them. And at the same time, she measured edge of field losses both in the surface and in the subsurface. James Kober, we divided the field into plots and planted different varieties of cover or different species of cover crops, and again measured runoff concentrations, not volumes, but concentrations in the surface and in the subsurface throughout the non-growing season. And so what James found is that when he looked at water extractable phosphorus in the plant material and in the underlying soils, and he compared this to overland flow, so that would be your surface runoff, in terms of the total phosphorus, dissolved reactive phosphorus, but also in the shallow subsurface flow and in the shallow groundwater below the surface. In the subsurface, it really didn't relate to anything. But in the surface, it tended to be more related to what was in the soils than what was released by the plants. So although the plants were releasing phosphorus, the soils were more strongly regulating what those concentrations were. When Tatiana went out throughout her annual cycle or her non-growing season, she looked at the cover crops and the soil. And in this graph, we're looking at water extractable phosphorus as a concentration. When we think about the biomass of the cover crop and the bulk density of the soil, although the cover crop per gram seems to be a much bigger source, when we actually look at the biomass, the top couple of inches of soil is a far greater phosphorus source to runoff than the cover crops themselves. And what we actually found is that yes, they experienced frost, but by the time that snowmelt period happened in earnest, much of the soil, much of the cover crop water extractable P had long been released to the soil throughout the winter. And because it went into the soil, it tended to be held onto the soil. And so what she actually found is that what we lost at the edge of the field was very, very small relative to what was released by cover crops. So because they had contact with the soil, even though they released phosphorus, it didn't translate to edge of field losses. So my closing remarks are that runoff and phosphorus, these do occur year-round in Ontario. In Ontario, we find that most of our water leaves through tile drains, but a lot of our phosphorus is leaving in surface runoff, especially particulate phosphorus. So there are opportunities to reduce phosphorus loss using cover crops. Although there is a risk of phosphorus release following freeze-thaw cycles, it really depends on freeze-thaw cycle magnitude, the species that you plant, whether or not you terminate them, and the degree of water contact that you have. And so we can optimize our use of cover crops to mitigate these risks. So my contact information is on the screen, and I look forward to any questions that you might have. Thank you.
Thank you. Appreciate it, Marin. Glad to have you join us this morning. Continuing the phosphorus and cover crop discussion, we're now going to go a little bit south, and our next presenter is Nathan Nelson. Nathan is a professor of soil fertility and nutrient management at Kansas State University. So good morning and welcome, Nathan.
Hey, good morning. Glad to be here, and glad that I guess I will say that I've lost internet a little bit here already this morning, so hopefully we can make it through this without internet disruption again. So, but I'm going to go over just real brief, kind of some of the highlights that I went through in my kind of longer extended version that's recorded online. And so if there are any questions left over, obviously ask questions, but there may be some additional, or there definitely is additional information online in that other presentation. So I'm going to jump right into the focus of our study. We have been receiving a lot of questions about cover crops as a best management practice for reducing phosphorus loss, and particularly had several producers here that were asking if they could use cover crops as a best management practice when they fall broadcast fertilizer. And we generally recommend producers subsurface apply phosphorus to reduce phosphorus losses and decrease environmental concerns. But we couldn't find really any information on how cover crops would interact with phosphorus placement. And when we really dug into it, we didn't find much information at all really on the effectiveness of cover crops to reduce phosphorus in no-till production systems. And that's what we deal with a lot down here. So we set up this study back in 2014 to address these questions. And some of the questions listed here, will cover crops reduce phosphorus loss from surface broadcast fertilizers in no-till, right? That was our kind of big question. But along with that, some more basic questions: are cover crops going to affect phosphorus loss in no-till at all, right? So if you've got a no-till production system, put out cover crops, what are they going to do for that phosphorus loss? And then how will our phosphorus fertilizer management affect phosphorus loss? We had some good data on that already, but it's still fairly sparse when it comes to edge of field monitoring data. And then finally, do cover crops change the decisions that a producer might make for the right time and right placement of phosphorus fertilizers? We did this experiment at a facility we refer to as the Kansas Agricultural Watershed Field Laboratory. We've got 18 1.2 acre plots. You can kind of see them the cover crop and non-cover crop make kind of a little patchwork across this hillside. With 18 plots, that allows us to do to evaluate 6 different management systems replicated 3 times. So this is a large plot replicated study, right? Edge of field runoff type study, looking at natural runoff from rainfall. We're looking at a no-till corn soybean rotation, 3 treatments for phosphorus management. One was a control where we applied no phosphorus. And then we had 55 pounds P2O5 broadcast in the fall, and that went on probably somewhere between November and January, right? So fall, winter, but application. And then 55 pounds of P2O5 at a 2x2 placement at planting. And then we have 2 cover crop treatments, either with a cover crop or without a cover crop. And our cover crop was primarily a small grain is what really survived. We had some wheat and rapeseed, triticale rapeseed, and then a year that I think was just wheat alone. Kind of depended upon what our planting conditions were when we went out to plant that cover crop and what we thought was going to really do well in the winter and the following spring. I guess a little note about our climate here. We have obviously cold winters, but we don't really get snow melt runoff, okay? We get a lot of freeze thaw cycles. And so right now, we're obviously freezing cold at like 0 degrees or below right now. But this weekend, we're forecast to be up in the 40s. Probably in the next few weeks, we'll be up in the 50s and then drop back down. So it's a lot of freeze thaw. And so we don't get a lot of snow melt or snowpack that builds up, right? Not a lot of snow in the winter anyway. So I'll jump into some of the results. First off, the effects of cover crops on runoff. This one bar graph here is just showing for each year of the study the total runoff from either the no cover crop plots or the cover crop plots. And we see that for the first 3 years of the study, no difference between our cover crop and no cover crop plots. In the 4th year of the study, much more runoff, much more rainfall that year. And there we did see an effect where the cover crops decreased runoff in that 1 year. So not a real consistent effect at all on the runoff volume. But what we did see fairly consistently is that we decreased runoff intensity pretty much every year, where our peak runoff rates from the cover crop plots were lower. The peak runoff time, or the time to that peak, was extended by about 7 minutes or so. And there was a tendency to have longer duration, about 45 minutes longer of runoff from our cover crop plots than without the cover crop. So that runoff is coming off a lot slower. And for sure, when you stand out and look at the plots, you're like, gosh, it sure seems like there's less runoff where we have a cover crop, but it's just that it comes off slow. And when we get into the results, that this pattern of runoff really impacts our results, okay? And so first off, with erosion, obviously, if you have less intense runoff, right, it's coming off slower, we have a lot less erosion. So here we see annual erosion losses caused by those cover crops, or a decrease in annual erosion, I should say, 60 to 70% decrease every year. Even in those years where we had very, very low erosion, it was still less with the cover crop. And then in the years where we had high erosion, again, 60 to 70% decrease. So the cover crops are doing a great job at managing, at decreasing erosion, even in these no-till systems where we felt like we were doing pretty good already in decreasing our erosion losses. Now, cover crops tended to increase dissolved reactive phosphorus, though, okay? And this is not due to freezing of cover crop tissue. Could be part of it, definitely. But like I say, it's probably more than that. Fairly consistent. Every year of the study, about 70% increased dissolved reactive phosphorus concentration in the runoff. Total phosphorus really depended upon the year. Some years total phosphorus was higher, some years total phosphorus was lower, but a mixed result there. Now, if we go to our fertilizer management, we see that fall broadcast consistently had higher dissolved reactive phosphorus concentrations. If we spring injected that, or if we put that in a 2x2 placement, we decreased our phosphorus concentration in the runoff by about 40%. Our total phosphorus dropped by about 30%. So there were minimal interactions between the, I won't get into all the details, but these main effects were pretty consistent throughout the study. And so we see that the cover crops tended to increase dissolved reactive phosphorus in our different fertilizer management systems, and our fertilizer management practices tended to have the same impact regardless of whether there was a cover crop or not. So in summary, we're looking at cover crops do great at decreasing runoff intensity, great at decreasing sediment and particulate P losses. They're increasing dissolved reactive phosphorus losses, and that could be, some of it could be phosphorus coming from tissue. We've looked at that in some lab studies. We've got field studies going on right now looking at cover crop species comparisons. There definitely can be some phosphorus loss from the cover crop tissue, depending on, from a variety of different factors. But also, we're slowing down that runoff. That could potentially increase our contact time, increase phosphorus desorption from our soils. That could be another mechanism that we're investigating. And then also, we're decreasing the amount of sediment in our samples. And so there's really not an opportunity for dissolved reactive phosphorus to reabsorb to any sediment in the runoff process, right? Once it's released, there's less mixing with sediment in that flow path. So a lot of different things going on here that could result in this increased dissolved reactive phosphorus. Short story is those cover crops are not a silver bullet for phosphorus. We still need to use other best management practices, and subsurface placement is an excellent option for that. We had a lot of people on this project. I can't talk about this without acknowledging all their help. I can't mention them all by name right now. And we had a lot of funding as well. And so appreciate all of our funding sources and supporters. And with that, I guess we'll go to questions.
Very good. Yes, thank you, Nathan, and thanks to also Lindsey and Marin for their presentations. And so we'll go now into the questions. I remind the audience to post your questions in Slido or upvote the questions that are already there. Because this session was all on cover crops, I will just ask the question, and maybe the three of you can decide who answers, or maybe all of you want to answer it. So the first question is, so planting a cover crop that is no winter kill rye versus one that is winter kill like oats or radish would tend to reduce surface phosphorus runoff?
So I'll just mention that real quick. So the first few years I mentioned we used triticale, we used radish, triticale rapeseed combination, some winter wheat. The last 2 years, I haven't presented that data, but last year and then this year here, we actually planted rye. We still saw the same increase in dissolved reactive phosphorus. I think it's more than just coming from the tissue. Now, but there could be other things going on there too. So that's my, here's my quick response.
Very good. And Lindsey and Marin, if you want to answer any of these questions, I guess just jump in, okay? If not, we'll just move on. The next question is, years ago, we were told permanent vegetative buffer strips in strategic locations will help decrease both particular phosphorus and soluble phosphorus, I suspect that's what it stands for. Without an ability to consistently harvest the vegetative growth, could these buffer strips actually be
Yeah, so I think,
phosphorus runoff?
whoops, sorry, I think my audio cut out. Did I interrupt you, Fabian?
No, you're good.
Okay. Yeah, I think actually the person who could best answer this question is not on the call, but there is a researcher, David Lobb, out of University of Manitoba, who has looked a little bit more into the buffer strip vegetation, specifically in kind of the colder, more northern winters, and that's sort of his opinion, if I'm remembering that correctly. And Marin, feel free to correct me if I'm misquoting David. But I think that, yeah, if you harvesting the vegetation is important once it gets kind of saturated and once it kind of picks up the runoff. So yeah, so I think it's a little bit going to be a little bit of a mixed bag, kind of like what Nathan was seeing with the cover crops in terms of how effective it's going to be.
Very good. This next question, I think, is more for Dan or Jeff Bedge, but so I'll just ask it. I don't know if you have any thoughts. Do I need to apply phosphorus fertilizer for my corn if my soil test shows 16 parts per million and I'm using a starter? I don't know if you guys have any thoughts on that, or we can just skip it.
I guess I can mention real quick. I know that I did look at this, based on our soil test recommendations here in Kansas. If you went with a sufficiency recommendation, we're looking at somewhere around 20 pounds of P2O5 for corn, depending upon what, that's based on our recommendations here in Kansas, which you could probably put down as a starter, right? So it's possible that a starter would supply, for our system, a starter could supply enough phosphorus in that situation. I think Jeff and Dan should definitely comment on this question for up there in Minnesota and your recommendation system.
Fabian, can you hear me?
Yep.
Yeah, so I would say that he's right. He probably doesn't need broadcast phosphorus. If his soil test is in that medium category, starter would be adequate. The rate of starter will depend upon how fast that soil test will decline into the low category or whether it'll stay in the medium category.
Very good. Thank you. In my previous life, I used to work with P&K, but now I leave it for the other guys that are doing all that work. And I focus on nitrogen. Is there a small cover crop species comparison for phosphorus release?
I don't know if one of the others want to talk. I don't want to, it sounded like Marin had some work there that she had published already on that.
Yeah, just the ones that we had done. So we'd looked at a range. We looked at the ones that are pretty common in Ontario, to look at the different species. And so again, we found certain things, like especially the oilseed radish and oat. So things that typically winter kill, we're going to release a lot more. Whereas some of the, like whether it's the oilseed, not oilseed, sorry, the vetch or the cereal rye or the red clover, they tend to fare better in terms of phosphorus release.
And I guess I'll say too, based on the lab experiments that Albert did, actually the cereal rye seemed to have the most just without any phosphorus applied, but then as you applied more broadcast fertilizer, then the differences between the species became less. So it's kind of like what Marin said during her presentation, there are some different factors that go into that.
I just posted in the chat, we have a study where we looked at, this was more of a lab study where we looked at different methods of, it was a greenhouse kind of lab study where we looked at methods of termination, freezing or herbicide or clipping, and a few different species. After that, we're out in the field right now comparing just grass species, because for us, or small grains, those small grains tend to be what really persist over the winter. And so we're looking at phosphorus release from rye and oats and wheat and triticale and barley and a few, anyway, a variety of small grains that people might choose for a winter cover crop. But I don't have results on that right now. Oh, does it say attendees cannot see what Nathan just posted in the chat?
Yeah, you said.
Oh, did I just went to the panelists?
The whole group.
Well, let me go to everybody here. There we go.
Very good.
Okay, thanks.
Yeah, thank you. The next question, you can see it there, I'll paraphrase, basically about sharing the message of cover crops and their effects on limiting nutrient and movement. How can we effectively do that at the local basin? Because a lot of the folks that may be doing this work are not necessarily attending this conference. Any thoughts on that?
Yeah, I think that's it. I think that's a challenging question. I wonder if I think this is something that Anna Cates is working on a lot, in her position. But yeah, I think there's just a lot of, people getting things out on the ground and getting people talking. I think it's really, kind of that peer-to-peer learning. As if we can get people talking to one another, which I know is super hard right now to be all in a room together and people chatting, but if people are growing cover crops, it can be very obvious as they're driving around town, and it's just a matter of those people being willing to talk to their neighbors. So
some thoughts. So in Ontario, we've had good experience with community leaders, just talking like coffee houses, or, well, not obviously during COVID, but certainly prior to the pandemic, we've had a lot of good luck with that. A lot of, again, field tours, field twilight tours, or just generally getting the message out there, demonstrations in the field and trying to go to different regions. And then we've also had opportunities for funding where farmers can apply for some basically assistance to try cover crops to see if they like it. And I think, yeah, we're working on it. It's just like Lindsey said, like, I think just get out there and get that message out there as much as we can. And yeah.
Great, thank you. Next question, will studies on phosphorus loss be continued, or do you have enough information? It would appear that cover crops are marginal at best with phosphorus loss in fields.
I think a lot of us are going to continue on with the research in different avenues to try to optimize. I think I think cover crops coupled with other things have some have potential benefits. Like I don't think, like Nathan said, they're not going to be a silver bullet, but yeah. So I know certainly we're going to be continuing on to look at some of this work.
Yeah, and I think, you know, the same thing. I'm definitely interested in keeping looking at how this applies in kind of the colder, especially in the colder climate in Northwest Minnesota, where we do have a lot more spring flooding. So some of those conditions that might be red flags that, you know, Nathan and Marin have identified could be potentially more of an issue here. But until we field test it, we really won't know.
Yeah, and we're continuing here. A few of the things that we're really going to be looking at is trying to understand more about the mechanisms that are at play in and how the cover crops are increasing this phosphorus, dissolved reactive phosphorus losses that we're seeing, right? So, and then as we understand the mechanisms better, we may understand how we can adapt our management in these cover crop systems to minimize phosphorus losses, as well as take advantage of some of the other things that are going on, some of the other benefits from cover crops. And so definitely cover crops have got a lot of benefits. We will continue. And then we're also looking at maybe reducing phosphorus application. So if we start to use more of a sufficiency approach for phosphorus management, how will the cover crops impact losses and our crop responses when we're trying to apply a very minimal amount of phosphorus? So.
Very good. Thank you all. We are out of time. There are a few more questions, so I would, and they're actually specific. Some of them are specific to our speakers. If you could just answer those in the Slido, that would be wonderful. Thank you again for your participation. So continuing on now with the program, we have Tim Redetz. He's going to talk about the work that they are doing with Discovery Farms and on-farm research. And by the way, Tim has been doing a lot of work behind the scenes, and so we appreciate him kind of taking double duty here and doing a presentation as well as keeping the conference running.
Well, thanks, Fabian. There's a lot of buttons to click on the back end here. So can you see everything?
Yes, and I can hear you.
All right. All right, sounds great. So I'm going to give a short overview of my longer presentation that is recorded. Just a little bit on Discovery Farms. If you haven't heard of Discovery Farms, it's a program that was started in Wisconsin, has migrated to Minnesota, Arkansas, Vermont, and the state of Washington. So a few different areas are now taking up the same approach. But we really focus on farmer-led, farmer leadership and water quality discussions, credible research, and communicating those results. And the type of research that we're doing, let's see if I can get this, is we're really focusing in Minnesota and Wisconsin anyway on edge of field surface runoff and tile drainage research and collecting that data 365 days a year. Unfortunately or fortunately for us, snowmelt is a huge part of our lives in this upper Midwest. So monitoring that is particularly hard, but very important for our water cycle here. So when we set up on the edge of the field, either for surface water runoff or for tile drainage, we're collecting the amount of flow, so like a volume measurement, and then sampling that water for sediment and nitrogen and phosphorus. So a quick summary of some of the larger messages that we've seen over our data collection. Runoff and tile flow happen. So I think we've collected 151 site years of surface runoff data and over 100 of tile flow data. And every one of those years, except for one, we recorded surface runoff or tile flow. So we just live in a region where we have excess water at different times of the year. And it's hard to really limit how much water we get and how much water that runs off our fields with the practices that we have. However, we can control what's in that water in terms of sediment and nutrients in the way we manage our fields and time our field operations. First, we recommend starting with the soil. So the first major thing that we see is needed in some spots is really protecting that soil from moving off the fields. And this is particularly critical in our cropping systems during that May to July time period. Across Minnesota and Wisconsin, we find over three quarters of our sediment loss happens during that May through July time period. So basically that period from planting to crop canopy is really, really critical for preventing soil loss. If we can protect our soils during that time period before our crops canopy, we're really going to limit the level of soil loss that we observe in our fields. However, depending on your location, your landscape, your climate, the level of protection is going to be different. So the level of protection for soil loss in terms of runoff water that we see in Northwest Minnesota is going to be different than it is in Southeast Minnesota. Next, if we're talking about phosphorus, we see most of our phosphorus movement through surface water runoff and not as much through tile drainage. And traditionally, it's thought that most phosphorus loss is with soil loss. But here in Minnesota and Wisconsin, we also have a significant fraction in the dissolved phosphorus fraction. So about 50% of our phosphorus loss throughout the year happens during snowmelt. And in that snowmelt time period, about 80% of that phosphorus is in the dissolved fraction. So that is really critical, and I'm thankful to be following the previous three presentations, which covered some of the issues on that we're looking into as well, in terms of increased residue amounts, cover crops, having an impact on that dissolved phosphorus during snowmelt, but also on timing of fertilizer applications, and in particular wintertime manure application. Rate of phosphorus application, if we're really increasing our soil test phosphorus levels to a place where we're up around that 50 to 100 parts per million soil test phosphorus level, we see an increase in dissolved phosphorus in our runoff water. And then also placement. Is there a way where we can, in areas that can handle maybe more soil disturbance, placing that soil test phosphorus below the soil surface is going to give us a better result in terms of dissolved phosphorus losses. Lastly, in terms of nitrogen, also timing and rate of nitrogen applications really can reduce losses, and knowing your tile nitrate levels are important. We recommend taking samples, figuring out where you're at, so we can see how good of a job our nitrogen management programs are doing. But we primarily see most of our nitrogen loss move through the tile system compared to surface water runoff. So moving on, after a quick overview, some continuing work we're doing within our Discovery Farms program. One of the more exciting studies we got going currently in Redwood County, Minnesota. We're looking at a paired basin study of a north and a south site, around 12.5 acres compared to 10 acres. At each of these sites, we have surface water runoff and tile flow monitoring. And for the last 3 years, from 2017 through 2020, these basins have been managed the same. And this is a corn-soybean rotation with limited tillage, no tilling our beans, and then spring vertical tilling are before corn. Our nitrogen source is fall anhydrous for the corn crop. And then for the last 3 years, a cover crop has always been flown on in late August. And this has been a cover crop mix of annual rye, oats, turnips, and radish. For the first 2 years, had really tough time with establishment, really tough time with that annual rye. He has since moved to flying on cereal rye with that mix and had much better results. Basically, the only growth he can get is with his cereal rye. So in the future, cover crops will only be flown on the north site and not on the south site, and cereal rye will be part of that cover crop mix that is flown on. And so here's a picture of this last fall is when the change occurred, where we had cover crops flowing on the North Basin and not on the South Basin. And you can see some cereal rye starting to establish there in November. So basically what we did for the first 3 years of study, we were trying to pair up the basins. This is a graph of looking at the total surface water runoff and tile drainage on a monthly basis. And you can see the one-to-one relationship line plotted there. So if all the data points fell on that one-to-one relationship, we would see that those two basins are equal in terms of runoff. We're also looking at sediment yield. And on this one, we see the North Basin has more of a sediment yield than the South Basin throughout this initial 3 years of monitoring. Phosphorus losses have been relatively similar between the two basins. It really lines up closely on that one-to-one relationship. And then nitrogen looks more closely related to the total flow and runoff, where we see a bit more on the south site than we do on the north site. So as we move into the future, when we look at the next 3 or 4 years, we're going to be looking at if we can shift this relationship between the two basins with cover crops, with that flown on application of cover crops. So if we see a similar relationship in this next 3 or 4 years, we're not going to determine an impact of cover crops. If we see a similar increase in nitrogen or similar levels of nitrogen in the South Basin and lower levels of nitrogen in the North Basin, where we do have the cover crops, we're going to determine an improvement from that cover crop. And then also on the flip side, look at potential declines in relationships. And what I think we're going to see, and I think we've seen in a lot of other research, is an increase in or a decline in nitrogen. I think there's going to be improvement in nitrogen losses due to the cover crops if we can get them established reliably on a year-to-year basis. I think the real question is, and we heard this in the previous 3 presentations, is the role of phosphorus, in particular that dissolved phosphorus, and how that cover crop is going to impact those levels. So along with this, we're also going to document yield impacts and highlight management considerations for those that want to follow along and learn more about how to establish cover crops in these corn soybean systems in Minnesota. So with that, I'll be around for questions for the Q&A session.
Very good. Thank you, Tim. Our next speaker is Kenny Bloomfield. He will be talking about climate change and weather, and he will be telling us that it's going to get warmer soon enough, right?
Yeah, you wish. You hear me okay, Fabian?
Yes, I hear
Okay.
you very well.
Okay,
I don't
very
see a
good.
presentation yet, though.
Okay, yeah, it's coming. It is coming. Let's see, where'd that go? Got too many things open, I apologize. There we go, and still not seeing anything?
Not yet.
Okay, I might have to, hang on, I have to try again. There we go. Okay, we're gonna back up though.
Yep, it's
Yep,
coming up.
okay.
Very good. Yep.
All right. So this is a nutshell version of the presentation that I gave that you may have seen recorded. I'm just going to break down to the kind of the essential elements. And yeah, we are getting warmer. And if we feel bad for ourselves here in the upper Midwest in Minnesota, I mean, look at what's been happening in Oklahoma and Texas and Arkansas and Missouri, where they aren't used to this kind of cold. They've been almost as cold as we've been. They had air temperatures were in the negative teens overnight. And they don't have any insulated pipes. Their septic systems have no protection whatsoever. And they're breaking records by in some cases, 20, 25 degrees. They're breaking records by 20 or 25 degrees. So we're pretty lucky. Okay, so we're just going to get to this kind of quickly here. Minnesota's become, when we look at the pervasive trends, Minnesota has become wetter and warmer. We've seen more precipitation, we've seen more heavy precipitation, and we've had warmer winters and nights. And when we look at the projections for future climate conditions in the middle of this century, we see more changes coming. So not just what we've already observed kind of holding steady, but further increases and plus some new ones. And we'll get to all of this very briefly. And then of course, people are interested in what all of this means for the 2021 field season, especially the early season. And our question as climatologists, and I think what this audience is really probably most interested in is, do the relatively dry conditions of recent months prevail, or are we undergoing another transformation where we get back into a wet period? And I'll talk about that in a moment. There's evidence on both sides there. Okay, so let's just look at the obvious. We've had more precipitation. We've had more precipitation in the last decade than we saw any other decade. I've kind of cut out a piece of southwestern and southern Minnesota here in this inset map, but we could have done this for any part of western, southern, even the entire state of Minnesota. 2019 was the wettest year on record, and it capped off the wettest decade on record. And I'm going to move up here. What this graph on the right is the frequency of days with 3 inches of rain or more for an average station in Minnesota. And you can see that the frequency has really increased. And it's not a straight line. We have our ups and downs and our variability built into the climate, but we've been seeing more precipitation and more heavy precipitation. And we've also seen warmer winter conditions. And this is something that people, you only have to think back 2 weeks, and we were in I wouldn't say unprecedented, but we were in an incredibly warm winter. Since November, December, and January were ranked in the top 10 for combined warmth. And so really we've only had this flip to cold conditions in the last 2 weeks. And the question is, how big of an influence is this going to have on the winter statistics and also on the future conditions in the near future? But when we look at our extended winters of November through March, they've warmed almost 4 degrees Fahrenheit just since 1970. The anomalous warmth has become more common. It's become more extreme. We've seen fewer of those really cold extremes. So as cold as it has seemed the past several mornings, I think anyone in this audience, especially people who've lived in Minnesota for decades, they know that this is something that used to actually be pretty common. I'm not saying that when, parts of northwestern Minnesota hit 35 below, that wasn't really cold, or that with the wind chills at -55, that wasn't really deadly. It's just that these are things that used to be more common than they are now. And now what counts as extreme used to be pretty normal, and what used to count as extreme for cold weather, we don't really see anymore. So those are the pervasive trends. There are other things we would talk about if we had more time. This is out in Milan in western Minnesota. You can see that the coldest day of the year just isn't as cold as it used to be. And I checked so far anyway, I think Milan hit -27 or 28 during this cold outbreak. So if you can see my cursor, that would be just above this lowest red dot, kind of up here. And if you just look left from there, you see that it's not all that unusual to get that cold in Milan. When we look at the climate projections, they basically tell us what we've seen, these warming winters and increased precipitation, that should continue. Don't take the details too literally on these projections, because these are ensemble projections, and they kind of taking the average of a bunch of different models. But on the left, we see typical location in Minnesota. If we think of having 1 to 2 days per year right now, typically, where you get 98th percentile precipitation, so a couple inches of rain in maybe northern Minnesota, maybe 2.5 inches of rain in southern Minnesota. And by the middle of the century, we would get on average about an extra day per year, with that kind of heavy precipitation. And you have to assume, of course, that there's variability built into that. So it's not going to be every year. It's that that'll be the long-term average increase in the frequency of those. There will be some years where we don't get any, and other years where maybe we get 6 or 7 of those days with really heavy rainfall. And we also see, even though we haven't really seen increases in extremes of temperature and heat in the heat department, that by the time we get to the middle of the century, we would expect more heat stress and higher temperatures. Okay, so now I want to just talk about this winter, this and the coming season, and what we're looking at here. And one of the things I wanted to point out is that just the last couple decades, there's been this kind of distinct boom and bust pattern in our spring weather behavior. And I'll let you decide which is the boom and which is the bust. But basically, if you look at the years that I circled, these are years where we didn't have a lot of late winter snow, and we were not in a drought, and so we got into the planting season and the early fieldwork season with relative success. And these ended up being good conditions and often resulted in really good numbers too. Meanwhile, if you look at not all of the big spikes, but a lot of these big spikes, these are years where we ended up with late season snowfall that kind of picked up in February and in some cases continued into May. And of course, that's bad news from, whether you're looking at runoff, kind of late spring runoff, and then timing some of that snow melt also with the incoming heavy precipitation season. These are generally bad conditions, and anyone could think back to 2019. I mean, there were cancellations galore. And what we want to be careful about is this thing, this polar vortex, because we all think of it as something that makes us miserably cold. But what it's more notable for is the kind of prolonged late season snowy periods, whether or not that extreme cold ever materializes. So the examples that I showed in the last graph of those poor seasons, those were all polar vortex seasons that ended up with a lot of snow. The cold only really materialized in 2 of them. And so the question is this where we are in 2021? We just had a polar vortex disruption. And the reason this matters is because we've been dry. The entire state is now at least abnormally dry. There's even some drought in parts of western and southwestern Minnesota. And if we continue the dry conditions, then we're looking at depleted soil moisture and more summertime heat stress and maybe even water shortages. So the next few months are critical. Now, here's what the Climate Prediction Center has outlooked for the February, March, and April, kind of the early growing period. Warmer than normal temperatures over Minnesota, or slightly more likely to be warmer than normal temperatures over Minnesota. And then kind of a mix between either above normal precipitation or equal chances of normal precipitation over the state. So there isn't much to go on with that. And our question is, does the warm winter prevail as had been forecast? Do we go back into this? Was this just a 2-week, 3-week blip, and we come out of it and we go back to where we were with warm, mild conditions and kind of a lack of precipitation? Or are we going to get into one of those polar vortex driven late winter wet periods with a lot of snow? Now, the benefits of that would be it could reverse our drought, which is something that
wrap it up.
Yep, this is the last slide. And the detriment of that would be that it's, nobody wants all that precipitation in May. So to summarize it, we're already wetter and warmer. We've had more precipitation extremes and warmer winters and warmer nights. The projections indicate that all that will continue, plus we might get hotter summers by mid-century. And what we're watching is what we just discussed. Is the is the cold and the eventually snowy conditions, will that predominate, or are we going to flip back to the mild and dry conditions that have dominated? And that's it for me. Thank you.
Thank you, Kenny. And I forgot to mention Kenny is from Minnesota DNR. We will now continue on, and our next speaker is Melissa Carlson. She is from the Minnesota Wheat on Farm Research Network. And she will be talking about the research that she's doing with spring wheat.
All right. Thank you, Fabian. You guys have my slide up?
Yes, you we hear you well.
Okay, thank you. Perfect. Like Fabian mentioned, my name is Melissa Carlson, and I am the on-farm research coordinator for Minnesota Wheat's on-farm research network. And so we are actually located up in northwestern Minnesota, in around the Red River Valley. So it's probably a little farther north than what I'm assuming most of the audience is probably in southern Minnesota. And so, oops, that automatically went. Okay. So what is the on-farm network? We do replicated on-farm strip trials funded by the Wheat Checkoff and partially by grants with Minnesota Soybean Council, AFREC, and MDA. And today I'm going to touch on two of our projects that looked at sulfur and variable rate nitrogen in wheat. So basically how our basic setup for a lot of the trials that we do, we're just looking at one or maybe two treatments versus what is usually a farmer practice or a control. And we have at least 3 to 4 replications that are randomized through the field. And these are done at field scale. So they're applied and harvested by the producers with their equipment or the co-op's equipment. And then at the end of the season, we measure the yield in a weigh wagon and get protein samples for our wheat too. And so a quick review of the sulfur project. Obviously the recording had a little bit longer, more in-depth presentation on these, but we looked at sulfur in wheat. The objective behind this was that there's been increasing incidences of sulfur deficiency in northwestern Minnesota, North Dakota, more so in corn, and then also some in wheat also. And so we wanted to look at comparing 100 pounds of sulfur as AMS applied in the spring versus just a regular urea control. Just looking at spring applications of fertilizer, and then looking at the yield and protein from those full field harvested strips. And this was done over 15 locations from 2017 to 2019 in a project done with AFREC. So quickly, kind of what we found in 2017, we didn't see a whole lot of, there was some slight differences in protein and test weight, but mainly we didn't see any differences in yield between the two treatments, the control and the sulfur treatment. And this was also the case in 2018. There was one location that had a difference in protein, but other than that, everything else was not different between the two treatments. And that's also what we saw for the most part in 2019. In 2019, we did have one location that responded, had over a 6 bushel yield increase due to the sulfur application. And that field was very light, very sandy ground, and had never had sulfur applied to it before. So it was definitely a field that was lacking in sulfur. But otherwise, the other field did not respond to a sulfur application. And so overall, when we're looking at those average field strips that are harvested across the whole field, we didn't actually see any response to sulfur fertilization in our wheat over the 3 years in the 15 locations. Part of this may have been just due to weather. We had enough sulfur mineralization from some of the organic matter to supply all of our sulfur needs. I know this is kind of similar to what Dan Kaiser had found in some of his small plot research, not really finding any responses to sulfur in wheat for sites that had over 3% organic matter. And we saw that even in our sites with 2 to 3% organic matter, we didn't have any much for responses. So this might be something to just keep an eye on and let your crop tell you what is going on in your field. It might just be localized. You might end up with just sulfur deficiencies, maybe on just small knobs or in depressions, depending on the season. But on average, overall, we didn't see any responses in our trials. Quickly going over a different project that we also had with AFREC as part of this grant, we looked at variable rate nitrogen applications in wheat. And I will let, hopefully those of you, or everyone was able to review the pre-recorded presentation to get a more in-depth look or explanation of how we made the maps. But basically we had 5 variable rate application maps with 5 zones, and we compared those variable rate strips to flat rate application strips of what the fertilizer would have been if it was just a whole field application rate. And this was also in wheat in northwestern Minnesota. And so we collected the yield maps from these trials and then also harvested our full field strips across all the management zones like we would with a normal trial to try and collect some grain quality data as well. Without going into each, this is just another explanation of the treatments. Without going into too much detail on each of the individual years, the gist of it is overall, combined overall the years, we didn't see a difference in the flat rate and variable rate nitrogen applications in the yield and the quality. But this was looking at that yield data and that protein data from those harvested field strips that were going across. All the management zones. So kind of the field average response was maybe a no difference between treatments. Something that I wish we did in 2019 that wish we would have done in the other years in 2017 and 2018 was look at residual nitrate in each zone in each strip. It's kind of like grid sampling each of the individual plots. We found a lot of variability in the residual nitrate amongst all those productivity zones. We didn't find any significant differences except for at one site, that Crookston field site. And that Crookston field site also had a positive yield response. So I dived into it just a little bit to take a closer look at that field. So that field actually had a 5 bushel yield increase from the variable rate treatment. And also had a higher residual soil nitrate in the high productivity zones of the variable rate nitrogen strips, where there would have been a lot more extra fertilizer applied. So just trying to look at the maps for this field, this would be an example of the application. So this would be the variable rate map originally laid out, and then so this would be the application map with those flat rate strips superimposed in those plots. And so there's kind of a summary. This map is a summary of the yield within each of those productivity zones that you can see outlined there. And here we kind of start to see that there potentially is some sort of productivity zone by yield interaction, which is sometimes hard to kind of make sense of when looking at maps. But just a couple of charts to also try and summarize it a bit. So here we saw that, again, there was a 5 bushel yield increase with the variable rate nitrogen treatments. And most of that came from those higher productivity zones were yielding higher. Those high productivity zones got about an extra 30 pounds of nitrogen compared to the flat rate treatment. And then here we saw that there was about 20 pounds more residual nitrate in those high productivity zones compared to the flat rate. So I think what we can kind of infer is that those higher productivity zones actually needed an extra 10 pounds of nitrogen to maximize their yield. So quick summary of final thoughts. So what we found when looking at that combine field data, when averaged across all of the management zones in those field strips, we didn't see any response to the whole field average response to the net nitrogen, variable rate nitrogen. But maybe there's more information at the zone level that we haven't teased out yet. And then one topic that I thought we could bring up for discussion in the Q&A if there's interest or if there's time is alternative methods for map making. I can review our methods for map making there, but maybe if folks had some time to watch the videos or maybe has some thoughts on variable rate nitrogen map making, we could talk about those as well. That was a really quick review, but that's what I have. So I think I will open it. I think I'm the last one, so I think we can open it up for Q&A.
Yes, thank you, Melissa. And yes, we are going into the Q&A now for our last 3 speakers. The first question is a good question that actually was covered last week during the nitrogen conference by Dr. Jeff Strzok, but I will ask the question. Is there any work being done to remove the nitrogen from tile drain lines and potentially reuse it?
Yeah, Fabian, I think I was going to mention Jeff too in his presentation last week. I think it did a nice job with this. I thought of two ways you could really think about this is with controlled drainage is a way people are doing this by holding back water during the growing season and having the crop actively use that. And then there's also some people, well, down in Arkansas, they actually collect all their drainage water and reuse that. And we've thought about trying that in our climate as well. The trouble is, we get a lot of our tile drainage from April through June and July, and having enough volume available for collecting all that water and then reusing it throughout the summer can be a challenge.
Very good. Next one is if you deep inject liquid manure, like in 6 inches in the tile system, is there a possibility of picking up the soluble phosphorus in the tile discharge water? And is this dependent on the depth of tile and type of soil?
Yeah, good question. We see this in northeast Wisconsin, and it does depend on depth of tile and type of soil. Typically where we see this is shallow tiles, and then soils that are prone to cracking are soils with clay with high shrink swell potential. And actually they recommend a pre-tillage before their applications of manure in some of their areas in northeast Wisconsin because of that issue.
This next question looks like it's for Kenny. Based on current climate data trends that have been recorded, what are a couple of management practices that you find to be the most critical to prepare for the challenges we may face in the future?
Yeah, sure. I did address this in the with the question too. I know this might not be satisfying, but I would say expect to be surprised, but also expect Minnesota to keep being Minnesota. So we will see these trends towards warmer conditions, but we're still going to have access to the coldest air on the continent. We're going to continue seeing trends towards wetter conditions, but we're just a wind shift away from having dry air imported from the Southwest and going into very dry conditions. So we should expand your expectations right now to something broader. And as you think about managing your land, you have to account for kind of an enhanced version of Minnesota with maybe not as much cold as we used to have. But when the cold comes, it might be kind of surprising, but more warmth, more water, but also more heat stress because of higher temperatures. So I would just say expand how you think of things currently to a broader, somewhat more extreme climate. And that's probably, and also review the science and talk to scientists about where climate projections are at with agriculture. Thank you.
Good, thanks. This is for Tim. Has there been any research or monitoring of phosphorus in fields that have high amounts of hog manure? When soil test levels get high, available phosphorus would appear to be a concern.
Yes, so not necessarily just hog manure, but we see when our soil test levels get in that 50 parts per million to 100 parts per million and above, we do see higher dissolved phosphorus concentrations in that runoff water.
Very good. This one is for Melissa. Will the carryover nitrate in the high productive zones negatively affect IDC in these fields or soybean next year?
I think that's definitely a possibility. Obviously, nitrate is one of the contributing factors to IDC, but I wouldn't say that it's necessarily going to guarantee that you're going to get IDC in the soybeans. Just depends on if it's, conditions in the spring are conducive to IDC for the soybeans, but it's definitely something to think about when you are fertilizing and making your maps. Keeping in mind that if you end up putting on a lot of nitrogen and you don't end up, if water or something else is yield limiting, you end up with a lot of residual nitrate. Thinking about that during the winter as you're going into how that's going to affect the soybeans the next season.
Very good. Kenny, this is for you. Is El Nino having an effect on our current late winter weather?
This would be more of a La Nina, the kind of opposite of El Nino effect, but also there's this other variation called the Arctic Oscillation, which is tied to the polar vortex disruptions. And that's the thing that's emerged over recent years too, as this kind of late winter disruptor that we're looking at. I think it's going to take a while for us to understand exactly what's been happening, but I would tie it more to La Nina and especially that Arctic Oscillation. It's a good question.
Should the farmer just consider sulfur to be very low soils, organic matter fields, or hedge the sulfur response? I think this may be a question for Tim, or maybe from some of our earlier speakers. Melissa, I'm sorry, this may for Melissa in terms of wheat.
Oh, yep. Sorry, that'd be towards my question. I would definitely consider, I think that would be a good option, trying to just hedge your bets, especially if you've got a light soil with low soil organic matter. You'd be maybe more likely to respond to sulfur. I know Dan Kaiser is also on. If he has any other comments to add to that, I'd more than welcome it. But I think that's probably a good way to go about it.
Yeah, about 10 pounds. If you want to look at applying some, maybe in that situation, particularly for wheat. Wheat isn't as responsive, so I don't recommend it as consistently, but I wouldn't go more than 10 pounds in that situation with some lighter soils. Just see if that improves yield.
Yeah, and the rates that we ended up putting on 24 pounds of sulfur, and that was intentionally a lot higher than what you would normally put down. So our rates were extra high for just the experiment.
This one touches on climate and weather, but I think it's more on a nutrient management kind of questions. Due to climate change, negative and also positive interactions can be found between nutrient availability and weather parameters in marginal lands for growing industrial crops. Under the context of climate change, how we can enhance nutrient availability in crop production? Any thoughts? I could pitch in a little bit of it. I work on nutrients, and one of the things I would say is that the biggest challenge really is in predicting what the weather will be like, especially with nutrients where the potential for loss is high and their high precipitation. That's the biggest challenge. So trying to delay applications as much as you can within reason so that you're not starving the crop for nutrients. It may be one way, because at that point when you apply nutrients, at least some of you already know what happened for part of the growing season. But even with talking about nitrogen, with late applications, we still have quite a bit of the growing season still ahead of us, and so it is definitely a challenge. So trying to match the application of whatever nutrient you're talking about with the time that the crop will need it is I think the critical factor, but it is a challenge. I don't know if any of the other speakers have something to add.
I could just add that I think we'll always be in a bit of a shortage or high demand for the right kind of weather information, and I'm not positive that the weather forecasting community is going to get a lot better over our careers at that kind of seasonal range outlook. So once you know what the conditions have been for a given season, you're kind of on your own. It's between you and the weather. It's just where climatology can help is with these longer term trends, where we can say, well, yeah, there's, you're more likely to be wet 6 out of 10 years and be warm 6 out of 10 years and things like that. But getting that precision that you need, that's all going to be a lot of money to be made in that branch of science integration.
Yeah, definitely looking at the odds is important. If you know that you will be more likely than not wet or losing nutrients in a particular part of the field or situation, then you kind of adjust based on that. And for us that do nutrient management, it's kind of nice to have a scapegoat and say, well, it's the weather. If we could predict the weather better, Kenny.
Yeah, and I guess I can't add much on the nutrient availability side, Fabian. I think you covered that well. But in terms of like the surface runoff side and tile drainage, our main questions on climate change is how is that going to impact our snowmelt conditions? Are we going to see more snowmelt because of fluctuating temperatures? Are we going to see less? And then also we see an increase of more intense rain fall events. How does that impact our soil loss levels and runoff that we observe?
Hey, Fabian, I'd chime in and say that one of the things that's concerning, not so much last year, but the previous several years, we had really wet falls. When we look at broadcast application, especially of phosphorus, the importance of either injecting it or incorporating it with some tillage in these really wet falls is a concern, or it's something we need to be thinking about.
For sure. Yep. The next two questions are for Tim. What rate of rye did you fly on? And the next one is about rate of barley. Which rate of barley will you fly on?
So I don't know about barley. I'm not a cover crop expert. The farmer that we were working with did fly on 1 bushel per acre of the cereal rye.
Next question is, what is the overall extent of research occurring in Minnesota on variable rate nitrogen?
That sounds like a good question for you, Fabian.
Yeah, so there is quite a bit of work being done in variable rate nitrogen right now. I know Brad Carlson and Yushin Miao are doing quite a bit with that. And then there are others that are as well doing some of that work. The challenge that we have seen is to see that consistent response to variable rate nitrogen, if it pays every time or how often does it pay. So that's where we are at right now, but certainly there is a lot of research right now looking at the variable rate using different technologies, canopy sensors and things like that. All right, next question. Oh, well, we are actually out of time. I'm glad I looked at the time. So there are more questions. If the speakers could please answer those in the Slido site, that would be wonderful. And we'll continue with the program right now. Our next speaker is Marisol Berti. She's from North Dakota State University, and we'll be talking about cover crops and nitrogen cycling.
Hi, thank you. Can I share the screen?
Yes, you can do that.
Okay. Can you see it now?
Yes, we see and hear you well.
Well, thanks everyone, and thanks for inviting me to this. I'm not a soil scientist, but we've been doing some work on nitrogen cycle with cover crops. If you saw my recorded presentation, well, I put a lot more information, so I'll do a little summary of the different research that we've done to do this. The nitrogen cycle, I know you've seen it many times, and from cover crops we know that, right? That we got nitrogen from the atmosphere, they can be fixed by legumes, and also we have cover crops, legumes fix nitrogen, but other cover crops, brassicas and grasses actually uptake residual nitrate from the soil. Okay, and these, as you can see in this picture, they're very low carbon nitrogen ratio, and in the books, in all of them say that these, once they decompose and scale in the winter, should release ammonia and for ammonium ions for the plant for the next season, the next crop. In this case, I put a corn picture. There's also some mineralization from organic matter to ammonium, and then this ammonium is nitrified to nitrate, and plants absorb nitrate, but also the plants can take ammonium directly too. And we fertilize the crops, and we're putting that ammonium in there. Now, we have all other processes where we lose nitrogen, but I didn't talk much about it because really I want to focus on what is happening here. So for some reason, what we think it should happen here is not happening, which is we're not be able to see the nitrogen from these cover crops into the next crop. And that's what these studies were for. I just put one of the slides I have about amounts, and cover crops, legume cover crops are also very good scavengers, okay? So whatever residual nitrogen it is from the crop before will scavenge nitrogen first and then fix. So here you see 4-HP nitrogen accumulated in the biomass is up to about 120, which about half comes from nitrogen fixation. This is planted in August 15 and harvested in November 15. Now, so all the legumes have a little bit of nitrogen fixation here, and then the brassicas for turnip and radish, all the nitrogen you find in the biomass is from scavenging, taken up from the soil. It's about 60 pounds. So we've done a lot of this work. We always find that cover crops, if you have the conditions for growing and you got water in the fall and you plant enough early enough, the cover crops take up significantly quite a bit of nitrogen. The problem is all the books would say that this nitrate should be available as a nitrogen credit for the next crop. And that's what we set up some studies to try to prove that. And if you saw my presentation recorded, we couldn't do that. And I just put a couple slides to show as a summary. So we tried to do this in both crops, corn and sugar beet. I'll show corn first. And corn, we have fava-bean, 4-HP, both legumes, and winter camelina, which is a brassica. So a scavenger and 2 nitrogen fixers plus scavengers. And what happened here is, again, these numbers are similar to what I showed you before, right? And we got 140 pounds per acre here in one of the locations, we got 4 environments, 2 locations, 2 years. And one thing is how much a cover crop takes up, it depends on the season, right? If we have rain or not, you can see there's a huge variability, location, season, what crop species, is a legume or a non-legume. So the nitrogen that's going to be in these cover crops is highly variable depending on the season. So some years we get a lot of nitrogen uptake, others we don't get much. Here camelina is not even there because it was so small we couldn't even analyze it. So the crop growth is what drives the nitrogen uptake, and the nitrate take up. And we're interested in that because we want to protect the nitrate from being leached. Now, when we look at the results, and this is not, several other researchers are finding the same thing. Dr. David Franzen in soils and in other states too. When we put different, so in the plots that we have cover crops next year, we planted corn, and then we put different nitrogen rates on those plots to be able to see this curve, right? And we see the check is that triangle, and you can see we increase the nitrogen rate to 160 pounds per acre, and we increase the yield, from very low to about 180 bushels. But when we had a cover crop on this plot, winter camelina, we actually have less yield, significantly less yield in all the rates. And this was mainly because of water use, but it could be other causes that we don't know yet. The only one that had some significant increase respect the check and some of the rates was 4-HP. So we saw a little bit of the nitrate that was in that 4-HP, maybe moving to the corn. But in general, there's no nitrogen credit. And so all we can say now is that doesn't matter how much nitrogen you have in the cover crop in the fall, it probably won't go to your corn. So you still have to fertilize your corn. In sugar beet, we did something similar, but the cover crops that we study are different. And they're different because, sugar beet, we were looking for different things here. So we had 3 winter crops because we're interested in protecting the soil from erosion, and also try to pick up some moisture early in the spring when we are really wet spring, so we can plant the sugar beet. And then we have these ones here. What happened? Again, well, we took up the cover crops depend on the crop, right? And we took some in the fall, and we added the spring. Of course, the winter crops survived and took up again in the spring, protecting that nitrate. So what is important is the water use in the spring, and because what we saw here is a root yield of sugar beet. In sugar beet, we only use 2 rates of nitrogen, 0 and 100 pounds per acre. And we really didn't see any differences between the rates. That's why I'm not showing it. But we did see in some environments, some of the winter crops had a reduction in yield, and some of the data I presented, some of the winter rye had a negative increase. And this was happened because in that spring, we had actually dry spring, and these winter crops actually took too much water, and so we had problems with establishment, and which resulted in lower sugar beet yield and also sugar, total sugar, recoverable sugar. These are pictures that were taken in July, and you can see here the pictures with the NDVI. You can see where a winter crop was, establishment is a lot less, and that's the reason for the lower yield. It's not that there's no plants here. The plants of sugar beet were there, but they were smaller. And so it took a while to catch up, and there was difference in yield, so they really didn't ever caught up on the season. So again, for sugar beet, we did not find any nitrogen credit going to the crop. And so in summary, cover crops can scavenge nitrate. We've had many experiments, and they do. You know, it's significantly higher than a control plot. But in this, how much accumulates will depend on the seeding date of the cover crop, water availability, soil residual nitrogen, cover crop species, if they're winter hardy or not. But we saw that we have to, when we have a dry spring, these winter hardy crops actually can negatively affect the cash crop establishment. There was some effect also on the corn, not as strong as it was for the sugar beet. But we cannot really find that nitrate in the biomass of cover crops that was in the fall, did not cycle to the next crop. And why, we still don't know. There's several theories, and that Dr. Franzen is trying to study, but we really don't know. And I thank you to all my team and Visiting Science and Postdoc and the funding sources for this project. So that's my presentation. I'll be happy to answer questions later.
Thank you very much, Marisol. Our next speaker is Anna Cates. She's from the University of Minnesota, and she will be talking about soil health measurements and what they tell us, these soil test measurements.
Hi, does it look okay?
Yes.
Okay.
Fine.
So I'm going to go over a few different measurements and essentially the goals we might have for them and how that might affect which measurements we might choose. I put this slide up just to kind of show the range of soil health measurements we might be talking about. Soil health is still this concept. It's not like your nitrate level. Everybody knows what that means in terms of a test. Soil health could still be tested any number of different ways, whether we're looking at a fairly expensive laboratory procedure or just looking at the soil and saying, oh, you know, there's some earthworms in there. I see some roots. The structure looks nice, and calling it good with that. So this kind of goes from the two possibilities, what they might give you. So I borrowed a few of these slides from Marshall McDaniel at Iowa State, because I think it does a nice job of laying out the possible purposes of a soil health test. So first of all, and I think this is some of the most common, especially in our research, we use a soil health test to show improvement in the whole soil ecosystem and its provision of ecosystem services over time. or after a change in management practices. So this is a lot of what you'll see out there. We're comparing cover crops and no cover crop fields, or we're comparing like some of Tim's studies, we had cover crops and then we don't over time. This one, I think, is where the rubber hits the road in terms of making an economic return on soil health tests and practices, is that it can inform another management practice like a fertilizer rate. And I'll talk a little bit about the capacity of these tests to reduce, to predict a reduced nitrogen fertilizer rate. And then the last one, which is really out there in the future, I would say, is increasing the farm income by providing proof that you have increased your soil carbon or increased an ecosystem service and selling that to a market. And the other piece of that in the long term is whether you can show that your land management has improved the land and therefore your land value should be higher. That's another really interesting long-term proposition. At this point, I would say that's most likely to maybe come to pass if yields increase with your soil health tests. So I'm going to talk mostly about the first function and a little bit about the other two. So this chart assesses how various soil health tests do in terms of that first function. So just to keep it clean for the beginning, the first list is what ecosystem service we're looking at. And all of these kind of mix public and private benefits, I would say. By public benefits, I'm thinking of things that the whole community benefits by, like reducing the nutrients in water in our local streams and also downstream in the Gulf of Mexico. But keeping water around in the soil rather than releasing it to the waterways is also good for farmers in a dry year, which, as we heard from Kenny, may be upcoming. So these are the different tests I'm going to talk about today. There's other tests you could look at too. The microbial biomass looks at all the biomass of microbes in the soil. And the way they've assessed this here is that microbial biomass is an indicator of soil stability because microbial biomass adds to aggregate stability. It's an indicator of carbon accrual because microbes are kind of the engines through which carbon is pumped into the soil. And it's an indicator of nutrient storage and release because microbes are the transformers of nutrients from their organic forms to their inorganic forms. So in the other columns, you can see that, for example, the CO2 burst test is only looking at microbial activity. So it's most focused on this ecosystem service. So these tests are each rated essentially by how many ecosystem services they might be able to reveal the effects of. Total carbon or soil organic matter can predict most of these, again, because total organic matter is related to soil structure. I saw in the comments on Slido that somebody thought that soil organic matter should also be related to nutrient storage and release, and I agree that that's a borderline possibility. I think the reason there's not an X there is because of the focus on nutrient release. So they wanted to look at the properties like the carbon dioxide burst test that measure microbial activity to show how fast nutrients are released. Infiltration related to water functions, decomposition of substrate related to nutrient release, aggregate slaking, soil structure, and then your senses. And I'll talk a little bit more about this because I saw there was a question about that too. But I think it'll be easier with the picture slides. So these are some of the carbon tests we're able to measure. This picture shows a food web of the soil organic matter carbon system underground. So you see that carbon flows from the plant roots into some of the larger organisms as well as into microbes and larger predators in the system. And the different tests get at different parts of this food web. The total soil organic matter or total carbon essentially looks at everything in there. The microbial biomass carbon separates out just the microbes, and the CO2 burst test looks at just the activity of the microbes and the other organisms, anything breathing out carbon dioxide. Decomposition of substrates, I put the undies in here. People do use things besides underwear to measure how fast decomposition happens. I think a couple researchers have talked about litter decomposition studies today. Aggregate slaking can be done in this visual form or else in a lab analysis that gets at how aggregates stay intact when they're submerged in water. And then infiltration is usually done by pouring a designated amount of water over a designated area to see how fast it sinks into the soil. Now for your senses, there's a number of things you could be using. I think a lot of people are looking for the same kind of structure that we're measuring with something like aggregate slaking. They're looking for how soil breaks apart in your hands. Another thing that's, I think, good to look at is the root health. That tells you something about how well roots are able to explore throughout the soil. And then things like color and things like looking for organisms like earthworms are also really relevant. So there's a real trade-off between accuracy and cost here. The way this scale is set up is that your measurement precision goes from low on the bottom to high on the top. So your senses are not very precise. I might see a soil is more brown than you. You might think it's better structured than I do. And something like microbial biomass, the carbon dioxide burst test are more accurate. However, they're also more expensive. They fall on the high cost side of the scale. And so you want to think about, well, which of these do-it-yourself measurements might be worth it to give me a little bit of information about what kind of changes I've been able to see in the soil versus wanting to have some hard data where you can show for something like that land valuation goal at the end, you might really need something that's more accurate. And it also might be worth it if you're going to get an economic return on that. So the next potential goal for soil health tests is to help growers make a management decision. I'm going to talk about nitrogen fertilizer management. This figure relates that carbon dioxide CO2 burst test that we're looking at with the food web slide to the economic optimum nitrogen rate. And note that here the CO2 burst tests are normalized from 0 to 1 because they took values from a couple of different studies with different methods. And the economic optimum nitrogen rate, remember, would be 0 when a test plot with no nitrogen added yielded the same as a test plot with sufficient nitrogen added. So like these ones down here, they essentially don't need nitrogen to perform at the same level as with a lot of nitrogen added. So that relationship really shows that as you have a higher CO2 burst test value, you needed less nitrogen in the soil. It's not that the R squared here is so perfect, it's only around 0.5, but we're not great at predicting nitrogen needs with other tests either. So within that sphere, this is not a terrible R squared value. This kind of zooms in on what that looks like for a couple of soils with a more standard economic optimum nitrogen rate curve here, where for soil B, which is one of these low CO2 burst tests, high EONR soils, shows that it's responding to nitrogen. And soil A, which had a low EONR and high CO2 burst, it's really not responding to nitrogen. It had sufficient nitrogen. And just to remind you, the mechanistic reason why that burst test is going to be related to nitrogen uptake is that the microbial activity is releasing organic nitrogen into inorganic form. So when we're measuring in the CO2 burst test how much carbon dioxide is produced, that's going to be related to nitrogen release too. So this last goal is kind of tricky and really future looking. I saw there are some questions about markets and credits. So we can talk about that more then. I know that the first farmers are set to receive some carbon credit payments either this year or in the coming year. At this point, the credits are based on adding new practices, and they assume changes in the soil properties like those discussed here. There are a few different companies with sort of different credit structures, but that additionality principle seems to hold true across most of them. And then the other piece of this is this land valuation. So this picture of a soils map here shows the crop productivity index based on Web Soil Survey. And the question is whether we can add to that what we know about land management from the last couple of decades. I think that this is happening on the local level anyway, where someone is deciding whether or not to buy a piece of property, knowing whether it's been beaten down or not. But it would be interesting if we could integrate some of these soil measurements to make that, to integrate that into essentially a crop productivity index there. I'm going to stop there, Fabian, and we can work into the questions.
Right, thank you, Anna. And we'll dive right into the questions for this section for Marisol and Anna. There we go. Anna, the first question is for you. How fast can we actually build organic matter?
I'm not going to hang my hat on any particular numbers on that one. I'm going to put in the Slido answer, though, this dashboard from the Nature Conservancy called Ag Evidence, where you can kind of explore different studies and see how in some cases soil organic matter has been built with different practices, and in some cases it's been lost. That really has to do with how much carbon is going in? Do you have a lot of residue and plant inputs going in? What's your climate? How fast is carbon mineralization happening? And it tends to vary a lot by soil type as well, because the physical structure of the soil is where that carbon actually resides. So I'll put a resource in there for people to explore that kind of thing, but I'm not going to give a specific number.
Okay, very good. Thank you. Marisol, did you test the cover crops or the soil for micronutrient content such as sulfur or zinc?
No, we did not. And we really don't have much of a problem. Soil tests for sulfur are not very reliable on really detecting deficiency. Also, usually we use more if we see symptoms, but none of these fields where we don't have any problems that we ever heard of sulfur or zinc. So yeah, we don't work much on micronutrients here. We're just trying to see mainly the nitrogen to see if we're getting any nitrogen credit.
Very good, thank you. When looking at soil health, is there a reliable method to determine what economic return a producer is getting from soil health measurements? Anna, what do you think about that?
Well, no, there's not a reliable method to determine that economic return. People have done some studies estimating the fertilizer value of increased organic matter, and that tends to plateau right around where a lot of our Minnesota soils are, around 2.5% or 3%. You don't see a huge yield increase after that. There are some interesting studies of sort of the long-term benefits of cover crops, and I'm working with a grad student right now to develop a spreadsheet that'll estimate that over 5 years and 10 years. So you may not get an economic return in that first year, but estimating how it might change over time. Marisol, I don't know if you have anything to add about what you've seen on your side of the border.
I can answer this next question, that same thing.
Okay.
Go ahead, Marisol.
Yeah. Well, yeah. We didn't see release in 1 year, but we know that nitrogen is going into the soil, and that's a good thing because it's feeding the microbes, right? It's just probably we have too short of a season, and also Dr. Francis finding, especially in the Red River Valley, we have these smectite clays that actually, when the soil is moist, the ammonia, which is a positive charge ion, goes into these layers, and when the soil dries, it traps it. So he's trying to prove that hypothesis, and so far he analyzed for non-extractable ammonia and actually found that the plots that have cover crops have a lot higher levels. So he might be into something there. So we know it's there. When it's going to be released, we don't. I haven't measured in the ones I presented. We didn't measure after that, but Dr. Francis has trying to follow similar experiments in 3 years in a row, and we don't find it. We really don't know. And so, but some years we've seen some differences. So I think it depends on a lot of things in moisture, but I think what's mainly happening, Anna, they might, your test or stuff, maybe we'll be able to modify what's the nitrogen credit in the long term that you can get. according to the soil health. Because directly we can't say, you know, you have this much cover crop biomass, you have this much nitrogen credit. It's just not happening. So thanks for the question.
Yeah, very good. And thank you for, you mentioned some of the work Dr. Franzen has been talking about with that ammonium getting into the clays and being tied up there. I would just mention that if folks want to hear his presentation, he spoke on that last Tuesday at our nitrogen discussion. And so that's available and they can view the recording of that. Next question. And this, Anna, you had talked about carbon credits. And the question is this from private companies or are these government programs that are promoting carbon credits and payments?
At this point, I'm only aware of private companies doing it. The American Farmland Trust had a good webinar last week where they had 4 different companies talk about their programs. If anybody wants to know the details, that would be a good place to start because they do vary just a little bit. And I think the devil's going to be in the details in terms of whether the data entry and sort of communication hassle for the grower is worth the payment. In terms of whether this will be tied to farm programs as a payment or requirement, I suspect we're far from that, but there may be some policy experts who have better insight as to the future of farm policy that way.
Yep, very good. I'm going to go to another question here. Anna, you had talked about the census as a soil health analysis tool, and you talked about some of the characteristics you might look for, but can you elaborate more specifically on what types of things to note, observe, look for when you're doing that census visual method?
Sure. I think looking at the structure in your hands is always a good start. And if you can submerge the soil in water and see how much clay is released from that, that's also a help. Another thing I think about in terms of using your senses has to do more with the whole seasonal observation. So what does your soil look like after a hard rain, after a light rain? Is the water infiltrating? Are you seeing runoff? And how fast is residue decomposing on the surface? Those are sort of the big picture functions that you can watch over the course of a year. Marisol, maybe you'd have something else to add about what people can look at.
We like smell the soil. You can, by the smell, you know, smells musty, really good smell when you have a good soil health. I don't know if you consider that in the census, but that's what I do.
Yeah, I think that's a great point.
Yep, smell is something that, you know, farmers often talk about when they're talking about soil health. There's a couple of questions left, and I would ask the presenters to take a look, and if there's something simple that they can put in as an answer or point them towards a resource on those unanswered questions, we'll do that. And then we'll move on to our next group of presenters. Next up, Brent Dalzell will be talking about some of the work he's done in the Cottonwood River watershed. Brent is a research soil scientist with the USDA Ag Research Service based here at the University of Minnesota in St. Paul. Good morning, Brent, and turn it over to you.
Good morning. Can you hear me okay?
Yep, just perfect.
All right, great, thanks. Get going here. All right, yeah, so as Warren mentioned, I'm a research scientist with the USDA ARS. Not too long ago, I was a research associate in the Department of Soil, Water, and Climate. So it was an easy move for me. I just had to pick up a box and move down the hall from my U of M office to my USDA office. And I'm looking to actually work in there in person one of these days. My U of M email is listed there. That's still a fine way to reach me. And this is work that I did with my colleague Jeff Strock, who's with the Southwest Research and Outreach Center in Lamberton. This work was funded by MDA, more specifically with money that came from the Clean Water Land and Legacy Amendment. And I just want to take a moment to acknowledge and thank our MDA colleagues who helped with this, Heather Johnson and Bill Fitzgerald and Peter Gillitzer and Brad Redlin. And then also importantly, the work that we did here builds on prior work and ideas that was supported by work on projects that were funded by the National Science Foundation and also Minnesota Corn Growers. So here's a snapshot of the Cottonwood River. This is in Flanders State Park near New Ulm. This is just upstream of the confluence with the Minnesota River Basin, or with the Minnesota River. And it's a nice area to go and check out the river. And it's almost easy to forget that if you go just a little bit upstream or a little bit out of the incised river valley at this point, you get into some of the most productive farmland in the upper Midwest. But that productivity does come at a cost. We know that, you know, nutrients in our waterways are not where we need them. And in a result of that, Minnesota has laid out a nutrient reduction strategy. That reduction strategy sets out pretty ambitious goals for decreasing the amount of phosphorus and nitrogen that's entering the upper Mississippi over the coming decades. And a lot of the heavy lifting from that is expected to occur as a result of changing practices on cropland. So there's a lot of conservation programs in place. CRP, for example, to try to encourage farmers to change practices on their landscapes to keep more nutrients on the field and out of our waterways. And the program that we are interested in for this study is the Minnesota Agricultural Water Quality Certification Program, MAWQCP. It's a bit of a mouthful. It's administered by the MDA. And for those of you that might not be familiar with it, what this program does is it provides farmers who are interested in participating, it provides them with priority for technical support and also access to cost share dollars to get farm-specific conservation practices that are tailored to their individual fields. In exchange for enrolling in the program, farmers achieve regulatory certainty for a 10-year period. So what that means is once you've become enrolled in the program, if Minnesota's environmental laws change, a new buffer law, for example, your farm is already deemed to be in compliance with environmental laws for that 10-year period. So there's a bit of a carrot and a carrot and a carrot approach to encouraging farmers to participate in this program. It's a pretty popular program. There's over 1,000 landowners enrolled in the program in Minnesota and over 715,000 acres certified. One thing that this program doesn't include is on-farm monitoring. With that many farms and acres, it would simply be labor and cost prohibitive and also invasive to the landowners to go out and monitor the actual water quality changes that result from enrolling in the program. But that doesn't mean we don't want to be able to quantify what those benefits are. And that laid out really the kind of impetus for this study. So the approach that we're taking to do that is through it's a modeling approach. We use a watershed scale model called SWAT. That stands for Soil and Water Assessment Tool. And it's a model that's set up specifically to evaluate water quality and quantity issues in agricultural landscapes. It's capable of simulating both overland flow and subsurface drainage processes, which if you're in Minnesota, it's important to get the tile drainage right if you want to get the right answers for the right reasons. Models are really useful for us. The SWAT model and many models keep track of major components of the hydrologic and nutrient cycles in soils and in watersheds. And this is useful for us because you can't measure everything everywhere all the time. It's just, we've not achieved the low cost instrumentation to achieve that yet. So we rely on models to help make sense of our field data and to fill in the gaps of the things we measure. But similarly, we rely on field observations to help constrain our models and make sure that they're behaving in a reasonable way. The place where this project diverges from more traditional modeling projects is that in general with watershed scale modeling, we start with a base set of spatial data like land use and soils and topography, but also some more broad assumptions about what typical management practices are in the landscape, time of planting and harvesting, fertilizer application rates, tillage practices, and things like that. But if you remember, our original question is, how is the certification program benefiting water quality? If we want to answer that specific question, we can't rely on these blanket sets of assumptions about management. Again, with one important part of models is calibrating them to make sure they're appropriate for local conditions. And so for that, we rely on important field data from long-term studies like the Discovery Farms data that Tim mentioned earlier, and data from the Research and Outreach Centers. Once the model has been set up, then we test it against observed data. So what I'm showing here is just a comparison of modeled flow against observed flow for the cottonwood. But there's a more rigorous set of comparisons that goes on to make sure the model is behaving the way it should. And then what's unique about this project and what the certification program allows us to do is we know in the Cottonwood River Basin in this example, but we know because the farmers are enrolled in the program what practices they were applying on their farms before enrollment in the program, and also what changes they made to their farms as a result of their enrollment in the program. And so this is kind of the highlights of that list for the landowners that are enrolled within the Cottonwood River Basin. The main changes that farmers implemented were changes in tillage, so conservation or no-till practices, modified fertilizer application rates, implementation of grass waterways or WASCOBs or water and sediment containment basins, cover crops, and also taking surface inlets and making them blind tile inlets. So we have specific information about what acres are enrolled in the watershed, and we have specific information from those farmer interviews as they were getting enrolled in the process that we can then go in and do some basically really careful bookkeeping and bean counting to modify practices on a field by field basis and then keep track of those changes. And this is a place where I go into greater detail in the previously recorded video. So I'm not going to go much here, but just that, this was a big part of the effort. But as a result of that effort, we're able to come up with quantitative estimates of nitrate and phosphorus and also sediment export for the enrolled acres in the watershed, but also on an annual or a year-by-year basis. And that's important because this allows you to also get a handle on the interannual variability, which is a challenge in Minnesota, as Kenny pointed out earlier. In the pre-recorded talk, you'll see some of these results in greater detail, but I just want to point out that for each of the enrolled farms, we give information for 3 different scenarios. One is what I refer to as a baseline landscape. And this is how that particular field or those acres would be characterized based on what we assume to be the typical management practices in the watershed. The orange triangles would be the farm-specific information. So this is based on the knowledge that we have as farmers were becoming enrolled in the program. And then the green circle is the farm-specific after the certification program changes. So there's a lot of information on a farm-by-farm basis here for sediment and phosphorus and nitrogen. And I'm just showing you those data here, but go back and watch the pre-recorded talk. And I'll just kind of give the broad overview here, which is that in general, certification program farmers are already implementing conservation practices on their farms or on their fields. And so that's shown here is the difference between that gray bar and that orange bar. So they're already practicing good practices. As a result of the certification program in the cottonwood, there were further reductions in sediment and phosphorus export. And that's primarily the result of water and sediment containment basins that were put on several of the farm fields that we looked at here. Interestingly, those same practices also caused a slight uptick in what the model predicted for lateral soil water flow and tile drainage volumes. And so that actually caused a small increase in simulated nitrate export. So I guess this was an approach that we thought allowed for a useful comparison of farm practices before and after enrollment in the program. And we think that this is important for helping to set realistic expectations for what kind of benefits we expect to see from enrollment in the program. And with that, I thank you for your kind attention.
All right, thanks, Brent. And we'll be back with Brent for questions in just a few minutes here as we wrap up. Our next presenter is going to be talking about soil properties and landscape position related to precision ag. Peter Kovacs is an assistant professor of precision ag cropping systems at South Dakota State University. Good morning, Peter.
Good morning. Hopefully everybody can hear me.
Yep, you're coming through good.
Okay, I'll try to share my slides. There we go. So today I will briefly summarize my previous presentation about how does landscape position or the landscape itself influence our crop management. And as you farming, most of you probably farming in Minnesota, these rolling landscape are not unusual. But have we thought that what difference can the different landscape position result in our management? And just an illustration, this is from my PhD study back from Indiana. And this was the year of 2012, which, if you recall, it was fairly dry, at least around the I-states. Maybe it wasn't as dry in Minnesota. But what we noticed in our study that at the relatively higher elevation, and we had about 5 foot elevation difference in this field, we noticed the huge yield differences. And probably this could be show up other parts of the field as well, or if you looking the yield monitor. Again, an aerial photography from a field from Indiana. And if we would have dug a hole and look at the soil profile at 2 different positions of the field, where we can see the different color patterns around within the field, probably we could have noticed some of the color differences even deeper. And if you recall some of your soil studies or some of your seminars, that these tan brownish color always indicate a better drainage compared to the gray and dark color. And following the normal pattern of water movement as it moves from higher elevation to the lower elevation, we can also assume that some of these darker spots probably are in lower landscape position. So there will be a little bit more moist environment in micro environment there, and likely there will be higher organic matter accumulation, which can also be seen on some of these darker colors. Many times we can have some sort of an estimation or guess what would be the drainage on different parts of the field. Again, where we see these darker color patterns, more likely we would assume poorly drained soils or some sort of a drainage issues, while at the top of the hill, more likely we'll have some well-drained soils. If we are in the environment like Minnesota or South Dakota, where we have plenty of wind, erosion could be another issue for those positions. And on the slope, we'll have moderately well or somewhat poorly drained soils, depend on how close we are to the top or the bottom of that slope. So if we look at some of the soil properties, what we could expect changes as our landscape position changes. If we have some erosion potential or we experience some erosion, more likely we'll have soil depth differences. We may even have some soil texture, and as the picture previously showed, that likely we'll see soil organic matter differences, and naturally we'll have likely some soil water differences between the positions. Now, knowing that nutrients will move with the help of the soil moisture or soil water, so that difference in soil water will likely also impact some of our nutrient availability. So if we look at the crop side, we can, in one side, could potentially look at water stress during the growing season, whether it's lack of water or excess of water. And likely we will see some impact on the nutrient availability related to those different positions. If you think about some of the lower positions, maybe we can even see a little bit more fungicide presence in those lower, likely more humid environment. So as we transition to the precision ag technologies and many service providers offer some grid sampling, one of the questions how we lay those grids relative to our landscape position, are we mixing a high versus a lower position, or are we trying to somewhat separate those different landscape positions and try to get the representative samples from those areas where we know likely our crop response will be different. And if we can identify some of these potential different management zones or management practices, what will limit our productions using GPS, hopefully we can start to think of different management scenarios based on the landscape positions. And again, if we think back, we shouldn't forget the basic agronomy. How can we minimize plant stress? So if we think more likely we'll have a water stress in terms of lack of water in higher elevations, can we select different hybrid or variety which could potentially handle these droughtier environment better? Or simply just changing the seeding rate can help minimize that extra or that water stress in our crop. And again, with that, if we're changing, are the nutrients or the nutrient requirements will be different in those fields. And same would be similar way for the depression zones, where we more likely would experience more of the excess water. So are we expecting year to year flooded or close to saturated environment in those micro depression areas? How can we potentially minimize our losses? If we think about some of the late spring, cooler temperatures, probably a little bit more moist soil conditions, would an extra seed treatment or in-furrow fungicide application help to go through on that emergence period and help out the young seedlings to emerge better? If we think about nutrient, and especially for nitrogen, where we would see more of the close to saturated or certainly a higher moisture level soil conditions, would a nitrogen stabilizer make sense to apply with those on those areas, or accounting for some of the nitrogen losses from those lower depression areas? Certainly, there are different ways how we could try to evaluate this, but one thing what I want to emphasize is having a multi-year analysis, if we have access to yield data, that how permanent are those low yielding or high yielding spots within our field, that we can see that over the years, those spots are showing up year after year. Probably you as a producer, you are aware of those lower producing spots or higher producing spots, but maybe a landscape position or the elevation can help us to explain some of that variation, and depend on what is the yield limiting factor or what challenges we're facing on those landscape positions, we can try to potentially differ or change on the management practices in those areas. I think I will wrap up here, and I saw a few questions already on the Slido yesterday, so I will hand it back to you, and then we'll go through on the questions, I assume.
Yep, very good. Thank you, Peter. And yes, we will switch over to the question screen. So the first question is for you, Peter. In your study, did you include any analysis of a return on investment or economic return for producers who invested and incorporated the use of multi-layered precision ag technologies?
Excellent question. Can I share back my screen again?
Yes, I think you can do that.
Okay.
Then
Good.
we'll go back to the question screen.
Okay. Because since I read this question, I forgot to include in my slides on the original talk, a colleague of mine at the Southeast Research Farm, they were comparing some of these upper versus lower landscape position using different varieties or hybrid both in corn and soybean with a modified twin row planter. So in that way, one of the row was planting in hybrid A, the other row planted a hybrid B. And what we could see that besides the different hybrids, they also changed the seeding rate. And you can see that some cases, the variable rate technology yielded a 5 or 6 bushel better on corn. And other years, there were no significant difference in between those different technologies. It would be similar for soybean. So based on going back to the question for the ROI, it will be fairly difficult to get the exact number because that will depend on each situation, that what is that yield variation, what you can experience within the field. Because probably if you have a larger yield differences, likely your ROI will be more likely than if you have just a couple of bushel differences between low versus high positions. The other thing, what I would think also, that how big is the extent of that area? So does it really make sense in terms of application, or can your equipment handle that small or large changes within the field? Because that's what we also have to consider.
Very good. And then a follow-up question, Peter, is there a formula or software that exists that incorporates these multiple factors into building the variable rate maps? Topographic, yield, soil type, and that sort of thing.
That is an excellent question. I have a feeling that probably there is no one button or one size fits all solution. So certainly the more common softwares on their advanced version, they have those multi-layer or comparison analysis, which should allow comparing your yields to different factors or different data layers what you have. But if you're interested for the topography only, potentially you can just classify the elevation, whether it's concave or convex, or some sort of a curvature analysis or a contour where you could overlay and see how similar your yield results compared to those elevation. I think that would be probably the simplest and easiest way to start with.
Okay, very good. Thank you. I'm going to skip down one and get a question in here for Brent. Brent, how would you increase grower awareness and benefits of the MAWQCP?
Yeah, that's a great question. So that the onus for that falls, back on MDA, and they do that through their MDA staff and also out at the county level with the district conservationists. I know that as a result of this study, they've launched into a more comprehensive study trying to get a handle on the economic benefits. So what are we the taxpayer, what are we paying for this program, and what are we getting out of that? That study is just getting going, so I don't have an answer for you on that, but I guess it's my hope that as we continue to kind of work down the pipeline in the science that follows from this, that more and more landowners will get enrolled. But with 1,000 landowners already and 700,000 acres, I guess that's a small fraction of what Minnesota has in production, but it's encouraging.
Just a follow-up to that then, Brent, what has been the BMP? And maybe, hopefully, maybe your answer will be there are several BMPs that you have seen implemented to assist in improving water quality across Minnesota.
Yeah, I'll steal a quote from Jeff Strzok here. He likes to say that there's no silver bullet, but there's silver buckshot. Yeah, I mean, I think, you know, the answer to that is it depends. You know, cover crops have shown a lot of promise for reducing nitrogen, and the nutrient reduction strategy goals for nitrogen are a little bit more ambitious than what they are for phosphorus. But at least for this work in the cottonwood, you know, the landowners that were putting in wascobs and grass waterways, they were seeing really big reductions in the sediment and phosphorus, which I think answers one of the Slido questions. It's a couple more down.
It does. It does. So yeah, one of the questions coming up is about conservation practices for phosphorus reduction. And I think this is specific to the cottonwood. And so you're suggesting that those wascobs might be one of the most effective?
When they're appropriately placed, yeah.
Sure. Okay. Thank you. Peter, is water and water movement one of the biggest underlying factors in yield variability for variable landscape positions?
Likely, yes, but probably each situation is somewhat different. Because if you think back on those eroded top hills, maybe the depth, soil depth will be another limiting factor. But considering that water will need for the plant and water is playing important role for nutrient uptake as well, likely that will be one of your biggest driving factor for that yield variability. Now, if we have a better year where we have a nicely distributed rainfall and timely manners, always just get that half an inch or 3/4 of an inch of rain, you may don't see as much yield variability between those landscape positions. So probably rainfall distribution and the water holding capacity, or the combination of those, will be the key for that.
Very good. Thank you. Next question, and Peter, you may have information on this. I'd also check to see if any of the other presenters who've talked about nitrogen today might look at this question and either chime in or add a little bit in a written response. But suggesting the nitrogen sensors that can be installed in the field to apply the nitrogen according to crop requirements. Can you suggest the type of nitrogen sensor that we'd be looking at? And similar to that, this person suggests they've installed a soil moisture sensor in the field to use for precision irrigation. And maybe you can talk about how those would interact.
I'm not sure that's how much my question or how much for Brent. Seems like a little bit more of the water related question too. It's a good idea, depend on what's your application methods, because I think most of the time if you look at try to lowering nitrogen load or pollution, yes, multiple applications, split application and targeted application would be appropriate. But I don't know how that comes back on the ROI side, whether going out 2 or 3 times or do these targeted applications during the season in smaller portion of the field, that may not be feasible at the moment. Now, with a UAV technology, that may be the future where we're going to go, that you can go back easily. In terms of sensors, that's a good question, and I may have to seek help from Daniel Kaiser if he's still around. Or
well, I see Fabian. Fabian, did you have something to add on that?
Yeah, so one of the biggest challenge, I mean, the technology is coming up, you know, where the sensors are becoming cheaper to produce, and there is quite a bit of work, not enough, but there is some work starting to happen to look at, you know, how reliable are the sensors. But the biggest challenge right now is in terms of variability, because you have to have a lot of those sensors installed in the field in order to get a good picture of what is happening, because nitrogen is variable. And so if you're relying on, you know, a couple of sensors in a field, you may you may not get a very good picture of what is happening for the entire field. So that's the biggest challenge right now. The other part too is that in terms of availability, early in the season, the sensors may may give you quite a bit of information in terms of what is available, but later as the crops start to take up a lot of nitrogen, the concentrations tend to drop pretty substantially. And so you end up with very low concentrations in solution, but that doesn't tell you anything in terms of the potential of the soil to supply more nitrogen.
Right. Okay. Very good. Thank you for that. I've got one last question here. Peter, what do you think about this idea? Targeted manure applications to the upper slope, low organic matter areas. Can that make a difference?
On theory, it would make sense to me. What I'm more cautious, or what I would caution the producer or the advisor, that how do we apply that manure? So if we want to capture all the nutrients, it would require incorporation or injection. And if we are already at that upper slopey area, how much extra erosion potential or how much we will increase that potential or increase the likelihood of the erosion for that part of the field. So if there is somewhere between the two, that applying more manure in those areas without too much soil disturbance, I think that could be a good idea. And maybe thinking back for the cover crop scenario, that could potentially increase some of the organic matter over time.
All right, very good. You're seeing now the Slido information. As we wrap up, we'll also put up the CEU information for you CCAs. There it is. And we'll give you a few seconds to log in and use the app to record your CEUs. Remember that if you're unsuccessful at doing that, you can always just put your name and your CCA number over in the chat box, and we'll pull those up and get those turned in as well. As we conclude today, I want to first of all thank Tim Raditz for all the work behind the scenes logistically, not just today, but over the last weeks with registration and all of that. So thank you, Tim. I want to thank Fabian again and Yabe Kiersgaard for helping to put together this program, contacting speakers and helping to pull all of this together. And it's been an interesting year doing it all remotely and virtually, but appreciate all of their help. I also want to thank all of you who presented today. Very good information, and now we've got it captured, and folks can go back and take a look at it as well. So a huge thank you to all of you who presented. And I especially want to thank our participants for being here, following along today. We welcome your feedback, and you should expect that the system will send out an email follow-up with a few brief questions to ask of you. We really would appreciate your response to that survey. You can help shape future conferences by telling us what you liked about this, suggestions for how we can make things work better in the future, and that sort of thing. So watch for an email in the coming days with that information as well. And then finally, if I didn't say so already, a huge thank you to our sponsors as well for helping us to by financially supporting all of the programs we've had here today. Fabian, Tim, do you have anything to add?
No, just simply a thank you to everybody, and to you, Warren, as well, for all the work that you put to put this event together. So it's been great, and we appreciate all the support that we've received from sponsors as well as you as participants. These events, the fact that you come to these events is telling me that you find value in the events, and we hope that we can continue to provide that information to you and help with nutrient management in your farms.
Yeah,
very good.
And I will just add, along with the survey that'll go out, I will also send out an email with our YouTube links of all the recordings of this meeting and also all the pre-recorded presentations, in case anybody either didn't catch the meeting or wants to go back and watch. I did see a question about still getting credits for watching the pre-recorded presentations. Unfortunately, we're not able to offer CCA credits anymore after this live meeting for the pre-recorded presentations.
All right, thanks for clarifying that, Tim. Well, with that, I think we'll sign off. Again, we thank you all for joining, and hope to see you in person for those that are able next year.